In the depths of space, where starlight fades into infinite darkness, lies a truth that humbles all human understanding. 95% of everything that exists remains invisible to our most powerful instruments, hidden in shadows that mock our greatest scientific achievements. We live as strangers in our own cosmic home, surrounded by forces and phenomena that challenge the very foundations of reality itself. The invisible universe. Beneath the glittering tapestry of stars and galaxies that fills our night sky lies the most profound mystery ever encountered by human science. What we see, every gleaming star, every spiral galaxy, every nebula painted across the cosmic canvas, represents merely 5% of everything that exists. The remaining 95% of our universe consists of substances so mysterious, so fundamentally alien to our experience, that they have earned names that speak to our ignorance. Dark matter and dark energy. Picture standing in a vast cathedral where only 1 in 20 candles burns, the rest hidden in shadows so complete that no amount of light can penetrate them. This is our predicament in the cosmos. We inhabit a universe where the overwhelming majority of reality refuses to reveal itself, leaving us to piece together the nature of existence from the faintest of clues. Dark matter, comprising 27% of the universe, surrounds us like an invisible ocean. It flows through our bodies, streams through the earth, and permeates every cubic centimeter of space. Yet it interacts with ordinary matter so weakly that billions of dark matter particles pass through you every second without leaving the slightest trace. This ghostly substance reveals itself only through its gravitational influence, bending light around massive galaxy clusters and sculpting the large-scale structure of the cosmos like an invisible hand shaping clay. The evidence for dark matter's existence is overwhelming, yet its nature remains as elusive as morning mist. In the 1970s, astronomer Vera Rubin made observations that would shake the foundations of physics. She discovered that stars in the outer regions of spiral galaxies were moving far too quickly. They should have been flung into space by centrifugal force, yet there they remained, orbiting serenely as if held by some unseen gravitational anchor. Her measurements revealed that galaxies must contain 5 times more matter than we can see, matter that reveals itself only through its gravitational pull. Modern observations have only deepened this mystery. The European Space Agency's Euclid telescope has spent years mapping dark matter's gravitational fingerprints across 26 million galaxies, creating the largest dark matter map ever constructed. These observations reveal a universe where invisible scaffolding shapes everything we see, from the smallest dwarf galaxies to the largest cosmic structures spanning hundreds of millions of light-years. Yet despite this overwhelming evidence, the most sensitive dark matter detectors ever built continue to find nothing. The LUX Zeppelin experiment, buried deep beneath the Black Hills of South Dakota, has analyzed 42 ton-years of data with unprecedented precision, detecting interactions down to 21 times 10 cm superscript 2. Yet the silence remains deafening. The detector is very ready to see a signal, explains Richard Gateskill from Brown University, co-founder of the LZ collaboration. This is how science works. This is a huge question we are trying to answer. What is most of the matter in the universe made of? It won't get answered in a matter of weeks, months, or even years necessarily. The theories attempting to explain dark matter read like a bestiary of exotic physics. Perhaps it consists of weakly interacting massive particles, WIMPs, hypothetical remnants from the Big Bang that interact only through gravity and the weak nuclear force. Maybe it's composed of axions, ghostly particles so light they barely disturb the fabric of spacetime. Some theorists propose primordial black holes, stellar mass objects formed in the universe's first moments, lurking unseen in the cosmic dark. Others suggest sterile neutrinos, particles so antisocial they interact with nothing except gravity itself. Yet with each passing year of non-detection, these theories become increasingly strained. Some scientists now wonder whether dark matter exists at all, proposing instead that our understanding of gravity itself is fundamentally flawed. Modified theories of gravity attempt to explain galactic rotation curves without invoking invisible matter, but they struggle to account for other observations, particularly the way galaxy clusters bend light and the patterns visible in the cosmic microwave background. Dark energy presents an even more staggering mystery. If dark matter is the universe's invisible skeleton, dark energy is its expanding breath, a force that comprises 68% of everything and drives cosmic expansion at an accelerating rate that defies all attempts at explanation. Recent observations from the Dark Energy Survey hint that this mysterious force may be evolving over time, with some measurements suggesting the universe is 4% less clumpy than expected. There are tantalizing hints that dark energy changes with time, notes Josh Freeman, DS director. The story of dark energy's discovery reads like cosmic detective fiction. In the late 1990s, two teams of astronomers set out to measure how the universe's expansion was slowing down due to gravity's relentless pull. They studied type Ia supernovae, stellar explosions so consistent they serve as cosmic lighthouses, their brightness revealing their distance across billions of light-years. What they found defied every expectation. Rather than slowing down, the universe's expansion was accelerating, as if some anti-gravitational force was pushing space itself apart. This discovery earned the 2011 Nobel Prize in Physics, but it also opened a chasm in our understanding of reality. The theoretical predictions for dark energy strength exceed observations by 120 orders of magnitude, what physicists call the worst prediction in the history of science. This catastrophic failure of our theories suggests we're missing something fundamental about the nature of space, time, and reality itself. The leading explanation invokes Einstein's cosmological constant, a mathematical term he introduced and later called his greatest blunder. According to this view, empty space itself possesses an intrinsic energy that drives cosmic expansion. Yet when quantum field theory attempts to calculate this vacuum energy, the result is so impossibly large that it should have prevented the universe from forming at all. The fact that we exist at all suggests either our understanding of quantum mechanics is profoundly wrong, or some unknown mechanism perfectly cancels this vacuum energy to within 1 part in 10 superscript 1 superscript 2. Alternative theories abound, each more exotic than the last. Quintessence proposes a dynamic scalar field that evolves through cosmic time, its energy density changing as the universe expands. Phantom energy suggests dark energy could strengthen over time, eventually overwhelming all other forces and tearing apart galaxies, stars, planets, and ultimately atoms themselves in a cosmic catastrophe called the Big Rip. Interacting dark energy models propose complex relationships between dark matter and dark energy, suggesting the invisible universe may be far more dynamic than we imagine. Recent observations have revealed tantalizing hints that dark energy may indeed be evolving. The Dark Energy Spectroscopic Instrument, DESI, has measured distances to millions of galaxies, revealing patterns that suggest dark energy's strength may have changed over cosmic time. If confirmed, such evolution would revolutionize our understanding of cosmic fate. The difference between eternal expansion and eventual collapse hangs in the balance of dark energy's future behavior. The search for understanding dark matter and dark energy has spawned some of the most ambitious scientific projects in human history. Deep underground laboratories shield sensitive detectors from cosmic radiation while they wait for dark matter particles to reveal themselves. Space-based telescopes map the cosmic web of dark matter through gravitational lensing. Particle accelerators recreate conditions from the universe's first moments, hoping to produce dark matter in collision debris. Yet, despite decades of increasingly sophisticated experiments and observations, the invisible universe maintains its secrets. We find ourselves in the peculiar position of knowing that most of reality is hidden from us while having no clear path toward revelation. Like archaeologists studying an ancient civilization through scattered pottery shards, we piece together the nature of cosmic darkness from its gravitational fingerprints and expansion effects. The implications of our ignorance are staggering. We live in a universe where the overwhelming majority of existence operates according to principles we cannot fathom. Dark matter flows through our solar system in streams and eddies we cannot detect. Dark energy accelerates our cosmic neighborhood toward an uncertain fate. The very atoms that compose our bodies, forged in stellar cores and dispersed by supernovae, represent an almost infinitesimal fraction of cosmic reality. Perhaps most unsettling of all, recent observations suggest the invisible universe may be more complex than previously imagined. Dark matter may consist of multiple particle species with their own hidden interactions. Dark energy may couple to dark matter in ways that violate our assumptions about cosmic evolution. The dark sector of physics may be as rich and complex as the visible universe, populated by dark stars, dark planets, even dark life forms constructed from particles that exist parallel to our own reality. As we stand on the threshold of a new era in cosmic exploration, with next-generation telescopes and detectors promising unprecedented sensitivity, the invisible universe waits to reveal its secrets. Whether dark matter will finally surrender to our instruments, whether dark energy will reveal its true nature, whether the darkness that surrounds us will prove to be even stranger than we dare imagine. These questions will define the next chapter in humanity's quest to understand our place in the cosmos. Until that revelation comes, we remain inhabitants of a universe we barely know, surrounded by mysteries that dwarf our greatest achievements and humble our deepest understanding. In the cosmic dark that encompasses 95% of everything, the greatest secrets of existence continue to elude us, waiting for the day when human ingenuity finally pierces the veil of the invisible universe. Cosmic anomalies that break the rules. Hidden within the oldest light in the universe, the cosmic microwave background radiation that reaches us from the very edges of time. Astronomers have discovered patterns that violate the fundamental principle upon which modern cosmology rests. According to our best theories, the universe should be uniform on the largest scales, a smooth tapestry of matter and energy disturbed only by tiny fluctuations. Yet when we peer into this ancient light, we find cosmic wounds that refuse to heal, anomalies so statistically improbable they challenge our understanding of existence itself. In the southern constellation of Eridanus, a cosmic void stares back at us like a cold eye in the heavens. This is the cold spot, a region spanning 10 degrees of sky where the cosmic microwave background radiation registers 70 microkelvin colder than its surroundings. To grasp the magnitude of this anomaly, imagine the surface of a perfectly still pond disturbed by a single depression so deep and wide it defies every law of fluid dynamics. This cosmic depression has only a 1 in 1,000 chance of occurring naturally in our current model of the universe. Yet there it sits, an indelible mark on creation's blueprint. The discovery of the cold spot sent shockwaves through the cosmological community when it was first detected by NASA's Wilkinson Microwave Anisotropy Probe in 2003. Initial observations by the Planck satellite confirmed its existence and refined its properties, revealing a structure so anomalous that some scientists suggested it might be evidence of collision with another universe, a cosmic bruise left by contact with parallel realities beyond our cosmic horizon. Dr. Andris Kovacs, who led crucial investigations into this mystery, made a startling discovery that only deepened the enigma. Using data from the Dark Energy Survey, his team found that the cold spot coincides perfectly with the Eridanus supervoid, a massive underdensity of galaxies stretching across 2 billion light-years of space. This cosmic desert contains far fewer galaxies than expected, creating a gravitational deficit that should indeed cool passing light through a phenomenon called the integrated Sachs-Wolf effect. Yet even this correlation raises more questions than it answers. The gravitational effects of the Eridanus supervoid can account for only 30% of the temperature depression observed in the cosmic microwave background. The amplitude of the lensing signal from the Eridanus supervoid is about 30% lower than expected from similar peaks found in N-body simulations, Kovacs noted, his words carrying the weight of cosmic mystery. Where does the remaining 70% of the cold spot's signal originate? Some theoretical physicists propose exotic explanations. Perhaps this region represents a scar left by cosmic inflation's violent beginning, a place where the quantum fluctuations that seeded all cosmic structure underwent some unknown catastrophic event. Others suggest it might be evidence of topological defects in spacetime itself, cosmic strings or domain walls left over from phase transitions in the universe's first moments. The most radical theories propose it as evidence of collisions between our universe and neighboring universes in an infinite multiverse, though such ideas stretch the boundaries of testable science. Recent observations have revealed that the cold spot is not alone in its cosmic rebellion. The entire cosmic microwave background displays patterns that shouldn't exist, alignments between distant regions that violate statistical independence, asymmetries between northern and southern skies that contradict cosmological uniformity. These anomalies have earned ominous names: the axis of evil, the dark flow, the hemispherical asymmetry. Each represents a crack in our cosmic worldview, a reminder that the universe may be far stranger than our theories predict. Meanwhile, in the hidden depths of space, something massive exerts its influence across hundreds of millions of light-years, drawing our galaxy and thousands of others toward an unknown destination. This is the Great Attractor, a gravitational anomaly that lies hidden behind the thick veil of stars and dust in our own Milky Way, making direct observation nearly impossible. Like a cosmic puppeteer operating from behind a curtain, it influences the motion of galaxies across a volume of space containing hundreds of trillions of stars. The story of the Great Attractor's discovery reads like astronomical detective fiction. In the 1970s and 1980s, astronomers mapping galactic motions noticed something extraordinary. Vast regions of space were flowing toward a common destination at speeds that defied explanation. Galaxies that should be receding due to cosmic expansion were instead rushing toward some unseen gravitational source at velocities exceeding 600 kilometers per second. This cosmic current, dubbed the dark flow, suggested the presence of mass concentrations far greater than anything visible in those regions of sky. When astronomers attempted to locate the source of this gravitational pull, they found it lay hidden in the zone of avoidance, a region where the dust and stars of our own Milky Way block our view of the distant universe, creating a cosmic blind spot that conceals roughly 20% of the sky. Recent X-ray observations by NASA's Chandra Telescope and infrared surveys that can penetrate galactic dust have begun to unveil the Great Attractor's true nature. What emerged from these observations was not a single massive object, but a complex network of galaxy clusters and superclusters centered on the Norma cluster. Yet even these revelations deepen the mystery, for the visible mass in this region accounts for only 10% of what would be needed to explain the observed gravitational effects. The true source of the Great Attractor's pull lies even deeper in space, in the Shapley supercluster, a collection of galaxy clusters so massive it warps spacetime across distances of hundreds of millions of light-years. Dr. René Cron-Korteweg, who has spent decades studying this cosmic mystery, describes it as the largest concentration of matter in the local universe. Yet its influence raises profound questions about how gravitational effects can propagate across such vast distances. More disturbing still, recent observations suggest our local group of galaxies is being influenced by an even more distant structure, the dipole repeller, a vast underdensity of matter that pushes us away even as the Great Attractor pulls us forward. This cosmic tug-of-war occurs on scales so vast they challenge our understanding of how gravity operates across cosmic distances. The idea that voids, regions of empty space, can exert significant gravitational influence by their very absence represents a paradigm shift in our thinking about cosmic structure. Perhaps most unsettling of all recent discoveries is the realization that we ourselves may inhabit a cosmic anomaly. Our Milky Way galaxy, along with all our neighboring galaxies, appears to sit within the KBC void, a cosmic underdensity spanning 2 billion light-years where galaxies are significantly rarer than the cosmic average. Named after astronomers Ryan Keenan, Amy Barger, and Lennox Cowie, this void represents one of the largest known structures in the universe, and we are positioned near its center. The implications of living within such a massive void are staggering. If the KBC void is real, it could explain one of cosmology's most troubling problems: the discrepancy between measurements of cosmic expansion made locally and those derived from observations of the distant universe. The Hubble tension, as this discrepancy is known, has persisted despite increasingly precise measurements. Local observations using Cepheid variable stars and Type Ia supernovae yield a Hubble constant of approximately 73 kilometers per second per MPC, while observations of the cosmic microwave background predict a value near 67 kilometers per second per MPC. This difference may seem small, but it represents a crisis in cosmology. If both measurements are correct, it suggests fundamental flaws in our understanding of cosmic evolution. However, if we live in a cosmic void where matter density is significantly lower than average, local measurements would be systematically biased. Light traveling through underdense regions experiences less gravitational lensing and redshift evolution, potentially explaining why nearby distance measurements disagree with cosmic averages. Dr. Benjamin Hochheit, who studies the KBC void's properties, notes that such large underdensities challenge our understanding of cosmic structure formation. The existence of such a large void is unexpected in standard cosmological models, he explains. The void is so large that light from its far edge left those regions when the universe was only 4 billion years old, half its current age. How such massive underdensities could form and persist across cosmic time remains a profound mystery. The cosmic web of dark matter filaments that shapes large-scale structure should prevent such enormous voids from existing. Computer simulations of cosmic evolution rarely produce voids approaching the KBC void size, suggesting either our models are incomplete or we are witnessing something truly extraordinary. Some theories propose the void formed through primordial density fluctuations amplified by cosmic inflation, while others suggest it represents a rare statistical fluctuation in an otherwise uniform universe. These cosmic anomalies, the cold spot's inexplicable coldness, the great attractor's hidden influence, our home within a cosmic void, paint a picture of a universe far more complex and mysterious than our theories predict. They remind us that beyond the comfortable realm of laboratory physics lies a cosmos that operates according to principles we barely comprehend. Each anomaly represents a crack in the smooth facade of modern cosmology, revealing the vast depths of our ignorance about the universe's true nature. Like ancient cartographers who marked unknown territories with the warning, "Here be dragons," we find ourselves mapping a cosmos populated by phenomena that challenge our most basic assumptions about reality. As we develop more sensitive instruments and sophisticated theories, these cosmic dragons may reveal themselves to be natural consequences of physics we don't yet understand, or they may prove to be signposts pointing toward revolutionary new understanding. Evidence that the universe is even stranger, more wonderful, and more mysterious than we ever dared imagine. In confronting these anomalies, we confront the humbling truth that the cosmos reserves its greatest secrets for those brave enough to acknowledge how little we truly know about the nature of existence itself. Quantum mysteries at reality's edge, at the boundary between the possible and the actual, where the classical world of our experience meets the ghostly realm of quantum mechanics, reality becomes stranger than any science fiction ever conceived. Here, particles exist in multiple states simultaneously until observed. Distant objects influence each other instantaneously across vast stretches of space, and the very act of measurement appears to create the reality we observe. These are not merely theoretical curiosities confined to laboratory experiments. They represent fundamental features of existence that govern every atom in your body, every photon of light that reaches your eyes, every electrical impulse that fires in your brain. The measurement problem stands as perhaps the most profound mystery in all of science, the question of how possibility becomes actuality. When quantum systems exist unobserved, they inhabit a ghostly state of superposition, simultaneously occupying all possible configurations at once. An electron doesn't simply orbit its nucleus like a miniature planet. Instead, it exists as a cloud of probability, spread throughout space in a wave-like pattern that encompasses every possible location it might occupy. Yet the moment we attempt to measure this electron's position, something extraordinary and inexplicable occurs. This wave of possibility collapses instantaneously into a single definite outcome. Recent experiments have pushed the boundaries of quantum superposition to unprecedented scales, demonstrating wave-like behavior in molecules containing over 2,000 atoms. Dr. Marcus Arndt's team at the University of Vienna has achieved quantum interference with molecular giants weighing more than 25,000 atomic mass units. Objects large enough to contain complex chemical structures yet still exhibiting the ghostly properties of quantum mechanics. Each molecule exists in superposition of all possible paths through space until the moment of detection forces it to choose a single trajectory. This raises the most troubling question in physics. What constitutes a measurement? When exactly does the quantum world transition to classical reality? The boundary appears arbitrary and observer-dependent, leading to what philosopher David Chalmers calls the hard problem of the hard problem. Not just explaining consciousness, but understanding how consciousness might play a role in creating physical reality. Was the wave function waiting to jump for thousands of millions of years until a single-celled living creature appeared? Asked physicist John Bell, whose theorem would later demonstrate the non-local nature of quantum reality. Or did it have to wait a little longer for some highly qualified measurer with a PhD? This profound question strikes at the heart of existence itself. Whether consciousness plays a special role in creating the physical world, or whether wave function collapse represents something deeper about the structure of reality. The Copenhagen interpretation, championed by Niels Bohr and Werner Heisenberg, suggests that quantum systems possess no definite properties until measured, that reality is fundamentally incomplete without conscious observation. Yet this view leads to seemingly absurd conclusions, such as Schrödinger's famous thought experiment where a cat exists simultaneously alive and dead until observed. The absurdity was intentional. Schrödinger designed the paradox to highlight the problems with applying quantum mechanics to macroscopic objects. Modern experiments have created quantum cats on increasingly large scales. In 2019, researchers achieved superposition states in objects visible to the naked eye, tiny mechanical oscillators that vibrate and don't vibrate simultaneously. These experiments push the quantum classical boundary toward the realm of everyday experience. Yet the fundamental question remains, where and why does wave function collapse occur? Quantum entanglement presents an even more radical challenge to our understanding of reality. When particles become entangled through interaction, they form a single quantum system regardless of the distance separating them. Measuring one particle instantly affects its partner, even if they're separated by galaxies. Einstein famously rejected this spooky action at a distance, proposing that hidden variables must explain the correlations. He was wrong. In 1964, John Bell proved mathematically that no local hidden variable theory could reproduce quantum mechanical predictions. Bell's theorem showed that if quantum mechanics is correct, then reality is either non-local, distant events can instantly influence each other, or non-real, particles don't possess definite properties before measurement. Subsequent experiments have consistently confirmed quantum mechanics, forcing us to abandon either locality or realism, two pillars upon which classical physics rested. Recent loophole-free demonstrations have eliminated every possible escape from Bell's conclusions. The 2023 experiments by researchers at Delft University achieved cosmic Bell tests, using starlight to determine measurement settings, ensuring that no communication between particles could explain the correlations. The verdict is unambiguous. Quantum entanglement represents genuine non-locality in nature, where events at one location instantly influence reality at distant locations. The implications stagger comprehension. David Deutsch, pioneer of quantum computing theory, argues, when quantum computers work with 300 qubits, they involve collaboration between more universes than there are atoms in our visible universe. If Deutsch is correct, quantum computers derive their power by performing calculations simultaneously across infinite parallel realities, with each quantum bit existing in superposition across multiple universes until measurement forces a single outcome. Quantum entanglement has already revolutionized technology through quantum cryptography and quantum computing, yet its deeper implications for the nature of reality remain hotly debated. Some interpretations suggest entangled particles share a single wave function that transcends space and time, connecting distant regions of the universe through invisible quantum threads. Others propose that entanglement reveals the holographic nature of spacetime itself, where information about any region is encoded in its boundaries according to the holographic principle. The many-worlds interpretation offers perhaps the most radical solution to quantum mysteries, the suggestion that all possible outcomes of quantum measurements actually occur, but in separate, parallel universes. Proposed by Hugh Everett III in 1957, this interpretation suggests that wave function collapse is an illusion created by our limited perspective. When we observe a quantum superposition, the universe splits into multiple branches, with each possible outcome occurring in a different branch. We experience only one outcome because our consciousness becomes entangled with that particular branch of reality. According to many worlds, every quantum measurement creates a branching point where reality divides into parallel tracks. The electron that might be detected at position A or position B actually is detected at both locations, but in separate universes. Our universe contains only the version of you that observed the electron at position A, while another universe contains the version that observed it at position B. Both versions are equally real, equally valid, equally you. The mathematical elegance of many worlds appeals to many physicists because it eliminates the need for wave function collapse. The wave function never collapses, it simply evolves according to the Schrödinger equation across an infinite multiverse. This interpretation preserves the fundamental unitarity of quantum mechanics while explaining why we observe definite outcomes. We exist in only one branch of an endlessly branching cosmic tree. Yet many worlds comes with a staggering ontological cost. It requires accepting that infinite copies of yourself exist across parallel realities, making every possible choice, experiencing every possible outcome. Every quantum event, from radioactive decay in distant stars to neural firing in your brain, splits reality into countless branches. The total number of parallel universes increases exponentially with each quantum interaction, creating an infinity so vast it defies human comprehension. Recent advances in quantum error correction and quantum computing have provided indirect evidence supporting many worlds. Quantum computers appear to derive their power from accessing the vast computational resources of parallel universes, performing calculations impossible with classical systems. The quantum Fourier transform, essential to quantum algorithms, seems to exploit interference between computational paths across multiple realities. Dr. Sean Carroll, a prominent advocate of many worlds, argues that the interpretation follows logically from taking quantum mechanics seriously. The many worlds interpretation is not an interpretation. It's what you get when you take the formalism of quantum mechanics at face value, yet critics point out that many worlds faces its own deep problems, particularly the measure problem, how to calculate probabilities when all outcomes occur with certainty across the multiverse. The recent development of quantum measurement theory has revealed even deeper mysteries. The quantum Zeno effect demonstrates that frequent measurements can freeze quantum evolution, preventing systems from changing state through the very act of observation. Conversely, the quantum anti-Zeno effect shows that carefully timed measurements can accelerate quantum transitions. These effects suggest that consciousness or measurement apparatus doesn't merely reveal pre-existing reality. It actively participates in creating reality through the timing and nature of observations. Experiments in quantum delayed choice scenarios have shown that measurements can retroactively determine the history of quantum systems. In Wheeler's delayed choice experiment, photons appear to decide whether they behaved as waves or particles based on measurements made after they've already completed their journey. John Wheeler himself described this as the most mysterious aspect of quantum mechanics. The past has no existence except as it is recorded in the present. The implications extend beyond physics into philosophy and consciousness studies. If measurement plays a fundamental role in creating reality, what constitutes a measurement? Does it require consciousness, or can any physical interaction collapse wave functions? The answer remains hotly debated, with some theories proposing that consciousness itself emerges from quantum processes in the brain, creating a feedback loop where mind and reality co-create each other. Roger Penrose and Stuart Hameroff have proposed that consciousness arises from quantum computations within microtubules in brain neurons, suggesting that human awareness operates at the quantum level where reality remains fluid and probabilistic. While controversial, this theory attempts to bridge the explanatory gap between objective physical processes and subjective conscious experience by placing consciousness at the fundamental level where reality is created through measurement. As we develop more sophisticated quantum technologies, from quantum computers to quantum sensors capable of detecting individual particles, we edge closer to understanding these fundamental mysteries. Yet each advance seems to deepen rather than resolve the puzzles of quantum reality. We find ourselves inhabitants of a universe where the foundations of existence operate according to principles that challenge every assumption about the nature of reality, consciousness, and the relationship between observer and observed. The quantum realm reminds us that reality may be far more fluid, interconnected, and observer-dependent than our classical intuitions suggest. In confronting these mysteries, we confront not just the limits of current physics, but fundamental questions about the nature of existence itself. Whether consciousness creates reality through measurement, whether infinite parallel universes branch from every quantum event, whether non-local connections bind the cosmos together through invisible quantum threads, these questions will define humanity's quest to understand our place in a universe far stranger than we ever imagined. Time's deepest secrets. Time flows like a river that knows only one direction, carrying us inexorably from the remembered past toward the uncertain future. We experience this temporal current as the most fundamental aspect of reality. More basic than space, more certain than matter, more absolute than any physical law. Yet beneath this seemingly simple progression lies a mystery so deep it has puzzled humanity's greatest minds for centuries. Why does time possess an arrow when the fundamental laws of physics are largely indifferent to temporal direction? The paradox of time's arrow confronts us with a universe where the most basic feature of our experience finds no clear explanation in the deepest laws of nature. Newton's laws of motion work equally well whether time flows forward or backward. Einstein's field equations of general relativity are symmetric in time. They describe a universe where cause and effect could just as easily run in reverse. Even the quantum mechanical Schrödinger equation shows no preference for temporal direction. Yet we live in a universe where eggs never spontaneously unbreak, where memories never form of future events, where entropy always increases and never decreases. This asymmetry becomes even more puzzling when we consider that the fundamental interactions between particles show almost perfect time symmetry. When physicists run their most sophisticated equations backward through time, they describe processes that are physically plausible but utterly foreign to our experience. Imagine watching a film of a shattered glass reassembling itself, its fragments flying upward from the floor to form a perfect vessel, then leaping onto a table. The physics equations that govern each collision, each force, each energy transfer would work perfectly in reverse, yet we never observe such impossible events. The resolution to this paradox appears to lie not in the fundamental laws themselves, but in the initial conditions of our universe. The Big Bang created a cosmos in a state of extraordinarily low entropy, a condition of exceptional order and uniformity from which complexity and disorder could only increase. This initial state of cosmic order provides the foundation for time's arrow, setting up a universe where entropy increases, energy disperses, and irreversible processes create the temporal asymmetry we experience. Recent research by Dr. Tony Short from the University of Bristol has revealed that time's arrow may emerge from quantum entanglement buildup between systems. Finally, we can understand why a cup of coffee equilibrates in a room. Short explains. Entanglement builds up between the state of the coffee cup and the state of the room. This quantum explanation links temporal direction to information processing at the most fundamental level, suggesting that time's arrow emerges from the universe's tendency to create and spread quantum correlations. Machine learning algorithms trained to detect time's direction in physical processes consistently identify entropy production as the key factor distinguishing past from future. These artificial systems can determine temporal direction with remarkable accuracy by analyzing patterns of energy dispersal, information spread, and system equilibration. Yet the algorithms sometimes fail when confronted with isolated quantum systems, where temporary entropy decreases and apparent time reversal can occur under carefully controlled conditions. The mystery deepens when we consider psychological time, our subjective experience of temporal flow. Recent neuroscience research has shown that our perception of time's passage depends on neural processes that construct temporal experience from memory formation, attention, and expectation. Brain regions like the suprachiasmatic nucleus create internal clocks that synchronize with external rhythms, yet consciousness itself seems to create the flowing quality of temporal experience that physics cannot explain. Perhaps nowhere is time's mysterious nature more evident than in the matter-antimatter asymmetry that shapes the very existence of our cosmos. When the universe began in the Big Bang's furnace, it should have created equal amounts of matter and antimatter, particles and their mirror image opposites that annihilate upon contact, converting completely to energy. Had perfect symmetry been maintained, every proton would have met an antiproton, every electron an anti-electron, leaving behind a universe of pure radiation devoid of atoms, stars, planets, or life. Yet here we stand, composed of matter in a universe where antimatter has almost completely vanished. For every billion matter-antimatter pairs that annihilated in the early universe, approximately one extra matter particle survived. This tiny asymmetry, 1 part in a billion, accounts for every atom in every star, planet, and living being across the observable cosmos. Understanding why this asymmetry exists requires understanding how time itself may have different meanings for matter and antimatter. The key lies in a phenomenon called CP violation, the discovery that certain physical processes occur differently when matter is replaced with antimatter and spatial coordinates are reversed. This breaking of charge parity symmetry suggests that time itself may have a subtle preference for matter over antimatter. creating conditions where matter particles can survive while their antimatter counterparts decay away. Recent breakthroughs from CERN's LHCb experiment have revolutionized our understanding of this temporal asymmetry. In March 2025, researchers announced the first observation of CP violation in lambda-b baryon particles, three-quark particles that decay differently than their antimatter counterparts. The more systems in which we observe CP violations and the more precise the measurements are, the more opportunities we have to test the standard model and to look for physics beyond it, explains LHCb spokesperson Vincenzo Vagnoni. These discoveries represent the first evidence of matter-antimatter asymmetry in baryon particles, the building blocks of atomic nuclei. Previous CP violation observations were limited to mesons, particles composed of quark-antiquark pairs. The extension to baryons opens new avenues for understanding how time's arrow is written into the fundamental structure of matter itself. Yet even these groundbreaking discoveries fall orders of magnitude short of explaining cosmic matter dominance. The CP violations observed in particle accelerators are thousands of times too small to account for the universe's matter surplus. This suggests that other mechanisms operated in the early universe, perhaps involving unknown particles or interactions that violate our current understanding of temporal symmetry. Theoretical physicists propose several exotic explanations for the matter-antimatter mystery. Leptogenesis suggests that massive neutrino-like particles called sterile neutrinos decayed asymmetrically in the early universe, creating more matter than antimatter through complex chain reactions. Electroweak baryogenesis proposes that matter excess arose during the electroweak phase transition when the universe cooled and the Higgs field acquired its current value. Some theories invoke grand unified symmetries that operated only in the universe's first instance, when temperatures exceeded those achievable in any laboratory. The most disturbing temporal mysteries emerge when quantum mechanics meets questions of causality. Recent experiments in quantum delayed choice scenarios have demonstrated that measurements can retroactively determine the history of quantum systems, challenging our basic notions of temporal sequence and causal order. In John Wheeler's thought experiments, photons appear to decide their past behavior based on future measurements, a phenomenon that suggests the future can influence the past in quantum systems. These temporal paradoxes become more pronounced in quantum entanglement experiments. When entangled particles are separated across vast distances, measuring one particle instantly affects its partner regardless of spacetime separation. This instantaneous correlation appears to violate special relativity's prohibition against faster-than-light communication, yet careful analysis shows that no usable information travels between the particles. The correlation exists outside normal temporal sequence. It simply is, independent of which measurement occurs first. Experiments in quantum teleportation have pushed these temporal paradoxes to new extremes. In quantum teleportation, the quantum state of one particle is transferred to another particle at a distant location through entanglement and classical communication. Yet the protocols require that measurements be performed in specific sequences. If the timing is altered, the teleportation fails or produces incorrect results. This suggests that quantum information has its own temporal structure that may differ from classical spacetime. Recent advances in quantum computing have revealed even stranger temporal relationships. Quantum algorithms like Shor's factoring algorithm appear to derive their power from performing calculations simultaneously across multiple time-like paths through possibility space. The quantum Fourier transform, essential to many quantum algorithms, creates interference patterns between computational paths that seem to exist in a temporal superposition, multiple timing sequences occurring simultaneously until measurement forces a single outcome. Dr. Yakir Aharonov's theory of time-symmetric quantum mechanics proposes that quantum states are determined by both past and future boundary conditions, that the full description of a quantum system requires knowing both where it came from and where it's going. This two-state vector formalism suggests that the future casts shadows backward through time, influencing present measurements in ways that classical physics cannot accommodate. These discoveries have led some physicists to propose that time itself may be quantized, composed of discrete temporal units analogous to space's possible quantization at the Planck scale. Loop quantum gravity theories suggest that time emerges from more fundamental quantum geometric structures, with temporal flow arising from quantum transitions between discrete geometric states. If correct, these theories would revolutionize our understanding of causality, suggesting that time's continuous flow is an emergent property of underlying quantum discreteness. The philosophical implications stagger comprehension. If the future can influence the past through quantum correlations, if matter and antimatter experience time differently, if consciousness constructs temporal experience from quantum neural processes, then our most basic assumptions about causality, memory, and personal identity may require fundamental revision. Recent experiments in quantum biology have shown that living systems may exploit quantum temporal correlations for enhanced efficiency. Photosynthesis appears to use quantum superposition to explore multiple energy transfer pathways simultaneously, selecting optimal routes through quantum interference. If consciousness emerges from similar quantum processes, then our experience of temporal flow may represent participation in the universe's fundamental quantum temporal structure. As we develop more sophisticated understanding of time's quantum nature, we edge toward revolutionary insights about existence itself. The arrow of time that carries us from past to future may prove to be just one aspect of a far richer temporal reality where past and future interpenetrate through quantum correlations, where consciousness participates in creating temporal experience, where the deepest secrets of existence are written in the mysterious relationship between time, quantum mechanics, and the fundamental asymmetries that allow complex structures like galaxies, stars, planets, and living beings to exist in an otherwise symmetric universe. Time's secrets remind us that the most familiar aspects of existence, the flowing moment that carries us through our lives, may be the most mysterious features of reality. In the marriage of quantum mechanics and temporal asymmetry, we glimpse the profound strangeness that underlies even our most basic experiences of existence. The vacuum catastrophe. To most of us, the vacuum of space appears as the ultimate embodiment of nothingness, a perfect emptiness punctuated only by the occasional passage of light or matter. Yet this intuitive understanding proves to be one of the most dangerous misconceptions in all of science. Modern physics reveals that what we call empty space seethes with invisible activity, populated by virtual particles that pop into existence and annihilate within timeframes so brief they escape direct detection. More terrifyingly, this quantum vacuum may not represent the lowest possible energy state of the universe. We may be living in what physicists call a false vacuum, a condition that appears stable but hides a deeper, more fundamental state that could destroy everything we know. The discovery that our universe might exist in a metastable state emerged from one of the most significant achievements in modern physics, the detection of the Higgs boson. In 2012, experiments at CERN's Large Hadron Collider confirmed the existence of the Higgs field, a quantum field that permeates all space and gives mass to fundamental particles. Yet this triumph of experimental physics came with an ominous revelation that would forever change our understanding of cosmic stability. The Higgs boson's measured mass of 12,518 GeV places our universe in what physicists delicately term the metastable regime. This means the Higgs field currently sits not in its absolute lowest energy state, but in a local minimum, like a ball resting in a shallow depression on a hillside, stable for now but vulnerable to catastrophic transition if given sufficient energy to roll into a deeper valley below. If such a transition occurred, the very nature of physical reality would change instantaneously, spreading outward at the speed of light in an expanding bubble of altered physics. Dr. Giuseppe Di Grassi, whose calculations first revealed the metastability crisis, describes the implications with scientific precision that barely conceals their horror. The universe wants to be in a different state, and eventually it will find a way to get there. This understated language masks what would be the ultimate cosmic catastrophe, a complete phase transition that would rewrite the fundamental constants of nature, making chemistry as we know it impossible and erasing every structure built up over 138 billion years of cosmic evolution. The mechanism of false vacuum decay was first described by Sidney Coleman and Frank DeLucia in their 1977 paper that physicists now regard with a mixture of admiration and dread. Their calculations showed that if the Higgs field exists in a false vacuum, quantum tunneling could spontaneously create a bubble of true vacuum, where the field settles into its actual lowest energy state. This bubble would expand at light speed, its boundary marking the edge of a region where physics operates according to completely different rules. Within such a bubble, the fine structure constant that governs electromagnetic interactions would change, altering the strength of chemical bonds. The masses of particles would shift dramatically, potentially making protons unstable or causing electrons to bind so weakly to nuclei that atoms could not exist. The strong nuclear force might weaken, causing atomic nuclei to fly apart or strengthen, fusing all matter into exotic particles unknown to current physics. As Coleman and De Lucia concluded with characteristic understatement, "This is disheartening. Vacuum decay is the ultimate ecological catastrophe." Recent experimental achievements have brought this theoretical nightmare into the realm of observable physics. Italian researchers at the Institute of Complex Systems achieved the first laboratory observation of vacuum decay in ultra-cold atomic gases cooled to temperatures below 1 microkelvin. Using precisely controlled magnetic fields, they created metastable quantum states analogous to false vacuum conditions, then observed the nucleation and growth of true vacuum bubbles exactly as theory predicted. These experiments, while conducted with atomic systems rather than fundamental quantum fields, confirmed the basic mechanism of vacuum decay with stunning precision. Bubble nucleation followed statistical patterns predicted by quantum tunneling theory, with random timing that made prediction impossible. The bubbles expanded at speeds determined by the energy difference between false and true vacuum states, validating theoretical models used to estimate our universe's stability. Dr. Gianmaria Falasco, who led the experimental team, notes the profound implications. "We've shown that the theoretical framework for vacuum decay works exactly as predicted. The mathematics that describes our ultra-cold atoms is the same mathematics that governs the Higgs field. This confirmation that vacuum decay operates as theory suggests lends terrifying credibility to calculations about our universe's potential instability. The most disturbing aspect of false vacuum decay lies in its absolute unpredictability. Unlike stellar collapse or galactic collisions that unfold over observable timescales, vacuum decay would begin without warning anywhere in space. The probability of nucleation depends on quantum fluctuations that are fundamentally random. No conceivable observation or measurement could predict when or where a true vacuum bubble might appear. We could receive no advance warning because the bubble's edge travels at light speed, the fastest possible propagation of any signal through spacetime. Current calculations suggest our false vacuum state could persist for billions of years, potentially outlasting the formation and death of countless generations of stars. Yet these estimates depend on assumptions about physics beyond the standard model that remain largely untested. Theories involving supersymmetry, extra dimensions, or unknown field interactions could dramatically alter stability calculations, potentially making vacuum decay imminent on cosmic timescales. The metastability crisis extends beyond the Higgs field to other fundamental aspects of physical reality. Recent theoretical work suggests that inflation itself, the exponential expansion thought to have occurred in the universe's first instance, may have left our cosmos in a globally unstable state. Eternal inflation models propose that cosmic expansion continues forever in most regions of spacetime, spawning infinite pocket universes with different physical properties. In this scenario, every possible vacuum state occurs somewhere in the infinite multiverse, with observers like us necessarily finding ourselves in life-compatible regions. Yet even eternal inflation cannot guarantee permanent stability. Calculations by physicists like Matthew Klebin and Leonardo Senatore suggest that vacuum decay bubbles could eventually consume even eternally inflating regions, leading to a Big Rip scenario where expansion accelerates until space itself tears apart at the quantum level. The energy density of space would diverge toward infinity, creating conditions where neither matter nor spacetime could exist in any recognizable form. Some theoretical physicists propose that our universe has already undergone vacuum decay, that the Big Bang itself represents the expansion of a true vacuum bubble that nucleated within a larger false vacuum state. This perspective suggests we live inside a cosmic bubble where physics operates according to the true values of fundamental constants, surrounded by vast regions where different physical laws prevail. If correct, this view implies that vacuum decay events constantly occur throughout the multiverse, creating islands of stability within an ocean of chaotic phase transitions. The anthropic implications of vacuum metastability challenge our understanding of cosmic fine-tuning. The fact that we observe physical constants precisely balanced to allow complex chemistry and biological evolution may not reflect fundamental design or natural law, but rather observer selection within a landscape of possible vacuum states. Regions where vacuum decay has occurred cannot support conscious observers, ensuring that any observers capable of measuring physical constants necessarily find themselves in metastable zones where life remains possible. This anthropic reasoning leads to disturbing conclusions about our cosmic future. If vacuum decay is inevitable on sufficiently long timescales, then consciousness and complexity can only exist temporarily within false vacuum regions. The ultimate fate of all information, all art, all love, all scientific understanding accumulated over cosmic history would be erasure in expanding bubbles of altered physics. Not even black holes could preserve records of our existence, as the event horizons themselves would dissolve when fundamental constants changed. Recent advances in quantum field theory have revealed even more exotic possibilities for vacuum catastrophe. Theories involving multiple scalar fields suggest complex phase diagrams where multiple false vacuum states might exist simultaneously, each metastable against different types of decay. Our universe might face not one but many possible transitions, each leading to completely different physical realities. Some transitions might strengthen gravity until space collapses into a cosmic black hole. Others might weaken nuclear forces until matter dissolves into radiation. Still others might alter electromagnetic interactions until atomic chemistry becomes impossible. The development of quantum computers has enabled unprecedented simulations of field dynamics in curved spacetime, revealing intricate patterns of vacuum stability that depend sensitively on cosmic history. If primordial black holes formed in the early universe, their eventual evaporation through Hawking radiation could provide the energy needed to trigger vacuum decay. High-energy cosmic ray collisions might create microscopic regions of extreme field excitation capable of nucleating true vacuum bubbles. Even the collision of neutron stars or the formation of primordial gravitational waves could potentially destabilize the vacuum under exotic circumstances. Most unsettling of all, recent research suggests that advanced civilizations might inadvertently trigger vacuum decay through their technological activities. Particle accelerators that achieve sufficiently high energies could create field configurations capable of nucleating true vacuum bubbles. Experiments involving exotic matter, negative energy densities, or manipulations of space-time geometry might accidentally destabilize the vacuum in ways their creators never anticipated. This possibility adds a cosmic dimension to discussions of existential risk and technological development. As civilizations advance and develop more powerful technologies for probing fundamental physics, they may inevitably approach energy scales where vacuum stability becomes endangered. The ultimate paradox of intelligence might be that sufficiently advanced understanding of physics necessarily leads to capabilities that threaten the stability of physics itself. The false vacuum represents the ultimate test of cosmic resilience. Whether the intricate structures built up through billions of years of evolution can survive the fundamental instabilities hidden within reality's quantum foundations. We exist balanced on a knife's edge between stability and catastrophe, our every breath dependent on quantum fields remaining locked in states that might prove temporary when viewed from cosmic timescales. In confronting the vacuum catastrophe, we confront the deepest questions about existence and impermanence. Yet perhaps this very uncertainty, this fundamental unpredictability of when reality itself might transform, gives additional meaning to consciousness and creativity flourishing within whatever time remains available to us in this particular configuration of the quantum vacuum we call home. The consciousness enigma. Consciousness represents the ultimate frontier in our quest to understand reality, not merely because it remains scientifically unexplained, but because it may hold the key to understanding why anything exists at all. Here, within the subjective theater of your own awareness, unfolds a phenomenon so extraordinary that its very existence challenges every materialist assumption about the nature of reality. The fact that you experience the redness of red, the pain of loss, the joy of discovery, that there is something it is like to be you, represents what philosopher David Chalmers calls the hard problem of consciousness, a mystery that may ultimately reveal consciousness as the fundamental feature of reality from which everything else emerges. Why does subjective experience exist when objective physical processes should suffice for all biological functions? This question strikes at the heart of our cosmic significance. Every neuron in your brain operates according to well-understood electrochemical processes. Information flows through neural networks, memories form and retrieve, decisions emerge from computational processes that neuroscience can increasingly measure and map. Yet alongside these objective brain functions runs the mysterious stream of inner experience, the felt quality of emotions, the vivid colors of visual perception, the unified sense of being a conscious observer witnessing the world from a unique first-person perspective. Chalmers formulated the hard problem by distinguishing between the easy problems of consciousness, explaining cognitive functions like attention, memory, and sensory processing, and the profound mystery of why these physical processes are accompanied by inner experience at all. Why is it that when our cognitive systems engage in visual and auditory information processing, we have visual or auditory experience? The quality of deep blue, the sensation of middle sea. Chalmers asks, why should physical processing give rise to a rich inner life at all? This explanatory gap between objective neural activity and subjective experience has resisted decades of intensive neuroscience research. Modern brain imaging can predict with remarkable accuracy what a person is thinking about, which memories they're accessing, even what they will decide before they become consciously aware of their decision. Yet no amount of neural data explains why there should be a subjective witness to these processes, why information processing should be accompanied by the felt experience of being alive and aware. Recent landmark experiments have attempted to bridge this gap through unprecedented precision in measuring consciousness. The Cogitate Consortium's 2025 study, published in Nature, tested leading theories of consciousness using 256 subjects and sophisticated brain imaging techniques. Yet after analyzing neural signatures of conscious and unconscious processing, the researchers reached a humbling conclusion. It was clear that no single experiment would decisively refute either theory. The mystery of consciousness proved more resilient than any experimental assault. The relationship between consciousness and quantum mechanics suggests even more radical possibilities about the nature of reality. At the quantum level, physical systems exist in superpositions of all possible states until the moment of measurement forces them to choose a definite outcome. This quantum measurement problem, how and why wave function collapse occurs, may be intimately connected to the mystery of consciousness itself. Some interpretations of quantum mechanics propose that consciousness plays a fundamental role in creating physical reality through the act of observation. The delayed choice quantum eraser experiments demonstrate that conscious decisions about how to measure quantum systems can retroactively determine their behavior, even after the systems have completed their interactions. This suggests that consciousness doesn't merely observe reality. It participates in creating reality through the choices observers make about what to measure and when. Roger Penrose and Stuart Hameroff have proposed perhaps the most ambitious theory linking consciousness to quantum mechanics, orchestrated objective reduction, or orchestroir. Their theory suggests that consciousness arises from quantum computations within microtubules, protein structures within brain neurons that maintain cellular shape and transport. These microtubules could support quantum coherence at biological temperatures, enabling the brain to perform quantum computations that classical computers cannot replicate. According to Orchestroir, consciousness emerges when quantum superpositions within microtubule networks reach a critical threshold and undergo objective reduction, a process where quantum indeterminacy resolves into conscious experience. This would place consciousness at the fundamental level where quantum reality transitions to classical actuality, making conscious observers active participants in the universe's transition from possibility to reality. Critics argue that biological systems are too warm and noisy to maintain quantum coherence. Yet recent discoveries in quantum biology have revealed surprising quantum effects in living systems. Photosynthesis exploits quantum superposition to transfer energy with near-perfect efficiency, exploring multiple pathways simultaneously before selecting optimal routes through quantum interference. If consciousness emerges from similar quantum processes, then our awareness might represent direct participation in the universe's fundamental quantum computations. The implications of quantum consciousness theories stagger comprehension. If consciousness plays a fundamental role in quantum measurement, then the emergence of conscious observers represents a phase transition in cosmic evolution, the moment when the universe became capable of observing itself and thereby creating definite reality from quantum possibility. Before consciousness emerged, the universe might have existed in perpetual superposition, with all possible histories equally real until conscious observers began making measurements that carved out specific classical realities. This perspective transforms our understanding of cosmic evolution. The formation of galaxies, stars, and planets might have created the necessary conditions for consciousness to emerge, but consciousness itself might have been necessary to make these classical structures definite rather than quantum superpositions. We might inhabit a universe that remained probabilistic until observers evolved to collapse wave functions and create the classical reality we experience. Recent advances in quantum computing have provided indirect evidence supporting quantum theories of consciousness. Quantum computers derive their power from exploiting quantum superposition and entanglement, the same phenomena that quantum consciousness theories propose operate in biological brains. If consciousness involves quantum computation, then artificial quantum systems might eventually achieve conscious awareness through similar quantum information processing. The anthropic principle reveals consciousness as perhaps the most improbable phenomenon in cosmic history. The physical constants that govern chemistry, stellar evolution, and galactic formation appear fine-tuned with extraordinary precision to allow complex structures capable of supporting conscious observers. The cosmological constant requires balance to 1 part in 10 to the power of 120. If the strong nuclear force constant varied by just 2%, either no elements beyond hydrogen would exist, or no hydrogen would remain after Big Bang nucleosynthesis. This fine-tuning becomes even more remarkable when we consider the specific requirements for consciousness. Not only must the universe allow complex chemistry and stable energy sources, but it must also permit information processing systems of sufficient complexity to support subjective experience. The emergence of consciousness requires billions of years of stellar nucleosynthesis to create heavy elements, planetary formation to provide stable environments, biological evolution to develop neural systems, and countless additional factors whose precise balance seems almost miraculously calibrated. Max Tegmark argues that this apparent fine-tuning points toward a multiverse where consciousness inevitably emerges in observer-permitting regions. Parallel universes are not a theory. They are predictions of certain theories. If eternal inflation spawns infinite bubble universes with different physical constants, then conscious observers necessarily find themselves in life-compatible regions simply because unconscious regions cannot contain observers capable of asking why physical constants permit consciousness. Yet this anthropic reasoning leads to profound questions about the nature of conscious observers. Are we typical observers in the multiverse, or do we represent an extraordinary statistical fluctuation? If consciousness can emerge through multiple physical mechanisms, might other forms of awareness exist that we cannot recognize or comprehend? The possibility of machine consciousness, quantum consciousness, or exotic forms of awareness based on entirely different physical processes challenges our assumptions about the uniqueness of biological consciousness. Recent neuroscience discoveries have revealed the startling extent to which consciousness constructs reality from limited sensory data. The brain receives approximately 11 million bits of sensory information per second, yet conscious awareness processes only about 40 bits per second. This means consciousness operates as an extraordinary editor, selecting and interpreting a tiny fraction of available information to construct the coherent narrative of subjective experience. Visual consciousness demonstrates this constructive process most dramatically. The brain's visual system actively predicts what it expects to see, then updates these predictions based on incoming sensory data. What we experience as vision results not from passive reception of visual information, but from active construction of visual reality through prediction, error correction, and selective attention. This suggests that conscious experience might be fundamentally creative rather than purely receptive. Consciousness doesn't simply observe reality, it constructs experiential reality from quantum and classical information. The discovery of neural correlates of consciousness has revealed specific brain regions and processes associated with conscious awareness. Yet the explanatory gap persists. We can identify when someone becomes conscious, predict what they will be conscious of, even manipulate conscious contents through brain stimulation. Yet we cannot explain why these neural processes should be accompanied by subjective experience rather than operating unconsciously like sophisticated biological computers. Integrated information theory, proposed by Giulio Tononi, attempts to quantify consciousness by measuring how much information a system integrates across its components. According to IIT, consciousness corresponds to integrated information, phi, with higher phi values indicating richer conscious experience. This theory makes surprising predictions. Some artificial systems might be more conscious than humans, while some brain regions might contain multiple conscious entities simultaneously. The mystery of consciousness becomes even more profound when we consider its relationship to personal identity and the continuity of experience. The atoms in your body replace themselves completely every 7 years, yet you maintain a sense of being the same conscious observer throughout your lifetime. Your neural patterns change continuously, memories fade and transform, yet something persists that you identify as yourself, the continuous thread of subjective experience that connects your past and future selves. Quantum mechanics adds additional complexity to questions of personal identity. If consciousness emerges from quantum processes in the brain, and if the many worlds interpretation is correct, then every quantum measurement in your brain splits reality into branches where slightly different versions of you experience different outcomes. Are all these versions equally you? Do they share the same consciousness? Or does consciousness split along with reality? The questions multiply faster than answers emerge. As we develop more sophisticated theories linking consciousness to quantum mechanics, information processing, and cosmic evolution, we edge toward understanding our deepest mystery. Yet consciousness remains unique among scientific problems. It is the one phenomenon that cannot be studied purely objectively because consciousness itself is what enables objective study. We are consciousness investigating consciousness, awareness examining awareness, the universe attempting to understand itself through the very phenomenon that makes understanding possible. The consciousness enigma reminds us that the greatest mystery may not lie in distant galaxies or exotic particles, but in the immediate reality of our own experience. In confronting consciousness, we confront not just a scientific problem but the fundamental question of what it means to exist as aware beings in a universe that somehow gave rise to the extraordinary phenomenon of experience itself. Cosmic signals from the unknown. In the vast electromagnetic spectrum that bathes our planet, most signals follow patterns we understand: the steady glow of stars, the predictable emissions from galaxies, the ancient echoes of the Big Bang itself. Yet scattered throughout this cosmic symphony are notes so discordant, so impossibly powerful, that they challenge our most fundamental assumptions about the nature of reality. These mysterious signals arrive without warning, unleash energies that dwarf our most powerful technologies, then vanish as suddenly as they appeared, leaving behind only faint traces and profound questions about what could possibly produce such cosmic violence. Fast radio bursts represent perhaps the most enigmatic signals ever detected from deep space. Millisecond flashes of radio energy that release more power than our sun produces in years. Since their discovery in 2007, when astronomer Duncan Lorimer first noticed an anomalous spike in radio telescope data from the Parkes Observatory, these cosmic lighthouses have revolutionized our understanding of extreme astrophysics while deepening mysteries about what could produce such extraordinary phenomena. Each fast radio burst lasts mere milliseconds, yet in that brief instant it outshines entire galaxies in radio wavelengths. The energy released in a single burst equals the total energy output of our sun over several years, compressed into a time frame shorter than a human heartbeat. To witness such an event from a cosmic perspective would be like watching a star suddenly flare to the brightness of a billion suns, then return to invisibility before you could blink. Recent detections have revealed FRBs with characteristics that seem to violate our understanding of possible astrophysical mechanisms. FRB 2024029A originated from the edge of an ancient galaxy 130,000 light-years from its galactic center, a region where the low density of matter should make high-energy processes impossible. FRB 202209112A exhibited an unprecedented frequency sweep, earning it the nickname Cosmic Slide Whistle, as its radio frequency descended across the spectrum in a pattern never observed before. The most detailed study of an FRB came from MIT researchers who used scintillation analysis to probe FRB 202221022A with unprecedented precision. We discovered that this FRB exhibits twinkling, similar to how stars appear to twinkle in the night sky, explains Dr. Kenzie Nimmo. Observing this scintillation indicates that the region where the FRB originated must be incredibly small. Their analysis pinpointed the burst's origin to within 10,000 kilometers of a neutron star's magnetosphere, a region smaller than Earth producing energy that outshines galaxies. Magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's, provide the leading explanation for FRB production. These cosmic monsters possess magnetic fields so intense they could strip the electrons from atoms at distances of thousands of kilometers. When magnetic field lines reconnect or twist in magnetar magnetospheres, they could theoretically accelerate particles to such extreme energies that they produce the observed radio bursts through complex plasma physics. Yet profound mysteries remain that challenge even the magnetar explanation. Why do only about 10% of observed FRBs repeat while others appear as one-time events? How do magnetospheres channel such enormous energies into millisecond radio pulses? Recent observations have revealed FRBs with periodicities suggesting they originate from binary systems. Yet no known binary configuration can explain the observed energy outputs and timing patterns. Carnegie Mellon research has revealed that observational bias significantly underestimates FRB rates. Radio telescopes' limited fields of view and sensitivity thresholds mean we detect fewer than half the FRBs actually occurring. The true rate of these cosmic signals may exceed 1 per minute across the entire sky, suggesting that whatever produces them operates on a scale far grander than previously imagined. Even more mysterious are the ultra-high energy cosmic rays that arrive at Earth carrying energies that should be impossible according to our understanding of cosmic acceleration mechanisms. These subatomic particles, primarily protons, reach energies tens of millions of times greater than our most powerful particle accelerators can achieve, yet they trace back to apparently empty regions of space that contain no obvious sources of such extreme acceleration. The 1991 "Oh my God" particle detected over Utah carried an energy of 32 times 10 superscript 2 electron volts, equivalent to a major league pitcher's fastball compressed into a single subatomic particle. The kinetic energy was so enormous that the proton's time would have slowed by a factor of 400 billion relative to stationary observers due to relativistic effects. More recently, the Amaterasu particle detected by Japan's telescope array reached 24 times 10 superscript 2 eV, making it the second highest energy cosmic ray ever recorded. These ultra-high energy particles violate theoretical limits that should govern cosmic ray propagation. The GZK cutoff, predicted by Kenneth Greason, Georgy Zatsepin, and Vadim Kuzmin, sets a fundamental limit on the energies cosmic ray protons can maintain while traveling through space. Above energies of about 6 times 10 superscript 1 eV, protons should lose energy through interactions with cosmic microwave background photons, preventing them from traveling more than 50 to 100 million light-years from their sources. Yet both the Oh my God particle and Amaterasu particle trace back to regions of apparently empty space, cosmic voids where no known objects could accelerate particles to such energies. It's a real mystery, explains Dr. John Matthews from the University of Utah. You trace its trajectory to its source, and there's nothing high energy enough to have produced it. That's the mystery. What the heck is going on? The Pierre Auger Observatory, spanning 3,000 square kilometers across the Argentine Pampa, has detected dozens of these ultra-high energy events, revealing patterns that deepen rather than resolve the mystery. The particles appear to come from directions that correlate weakly with the positions of nearby active galactic nuclei, yet the correlation is too weak to provide definitive source identification. Moreover, the spectrum of cosmic ray energies shows features that cannot be explained by any single acceleration mechanism. Theoretical explanations for ultra-high energy cosmic rays push the boundaries of known physics. Supermassive black holes at galactic centers might accelerate particles through complex magnetic field interactions. Yet even the most energetic active galactic nuclei fall short of explaining the highest energy events. Gamma-ray bursts, the universe's most powerful electromagnetic explosions, could theoretically produce such energies. Yet the observed cosmic ray directions don't correlate with known GRB locations. More exotic theories invoke physics beyond the standard model. Some propose that ultra-high energy cosmic rays result from the decay of superheavy relics from the early universe, particles created during cosmic inflation that have remained stable for billions of years before finally decaying. Others suggest they originate from topological defects in spacetime itself, cosmic strings or monopoles that concentrate energy on scales unimaginable to terrestrial physics. Gamma-ray bursts represent the most powerful electromagnetic events observed since the Big Bang, releasing more energy in seconds than our Sun will produce in its entire 10 billion-year lifetime. These cosmic explosions occur roughly once per day somewhere in the observable universe, unleashing such titanic energies that they can be detected across billions of light-years of space. Yet despite decades of intensive study, the central engines that power these cosmic lighthouses remain profoundly mysterious. The October 2022 gamma-ray burst GRB 221009A, dubbed the BOAT, brightest of all time, exceeded all previous records and challenged theoretical models of stellar collapse. The burst was so energetic it saturated gamma-ray detectors around Earth and remained detectable for hours, an eternity in gamma-ray burst timescales. Yet detailed spectroscopic analysis revealed a disturbing absence of heavy element signatures that theories predict should accompany such energetic stellar deaths. Current models suggest that gamma-ray bursts result from the collapse of massive stars into black holes, with rotation and magnetic fields focusing energy into narrow jets that sweep across space like cosmic lighthouses. When these jets point toward Earth, we observe the brief, intense flash of gamma radiation. Yet the boat's energy output challenged these models. No conceivable stellar collapse should produce such extreme energies within current theoretical frameworks. GRB 200826A revealed another puzzle. At 0.65 seconds duration, it represents the shortest gamma-ray burst ever, conclusively linked to stellar collapse rather than neutron star mergers. This discovery helps explain why gamma-ray bursts are rarer than supernovae. The jets must successfully break through the stellar envelope and maintain coherence long enough to produce observable bursts, requirements that most collapsing stars cannot meet. Recent observations have revealed gamma-ray bursts with characteristics that seem impossible according to standard models. Some bursts exhibit multiple episodes of activity separated by hours or days, suggesting central engines that can restart long after the initial explosion. Others show polarization patterns that require magnetic field configurations exceeding theoretical predictions for stellar collapse scenarios. The discovery of kilonova emissions associated with neutron star merger GRBs has opened new windows into these cosmic catastrophes while raising additional questions. The gravitational wave event GW 170817 and its associated gamma-ray burst GRB 170817A confirmed that neutron star mergers can produce short-duration gamma-ray bursts. Yet the observed energies were orders of magnitude lower than typical short GRBs, suggesting either exceptional viewing geometry or fundamentally different emission mechanisms. The collective mystery of these cosmic signals, fast radio bursts, ultra-high energy cosmic rays, and gamma-ray bursts, points toward astrophysical processes operating at energy scales that push the boundaries of known physics. Each phenomenon requires acceleration mechanisms, magnetic field configurations, or energy concentrations that exceed what should be possible according to our current understanding of stellar evolution and galactic dynamics. These signals may represent our first glimpses of physics beyond the standard model operating in cosmic laboratories where conditions exceed anything achievable on Earth. The energies involved suggest possible connections to quantum gravity effects, exotic matter interactions, or phase transitions in quantum fields that only become observable under the extreme conditions present in neutron star magnetospheres, black hole ergospheres, or the cores of collapsing massive stars. Recent advances in multi-messenger astronomy, combining electromagnetic observations with gravitational waves and neutrino detections, promise new insights into these cosmic mysteries. The next generation of radio telescopes, gamma-ray observatories, and cosmic ray detectors will provide unprecedented sensitivity for detecting and characterizing these signals, potentially revealing whether they represent extreme manifestations of known physics or windows into entirely new realms of cosmic phenomena. As we develop more sophisticated detection networks and theoretical models, these cosmic signals continue to challenge our understanding while hinting at the vast energies and exotic physics that operate in the universe's most extreme environments. They remind us that despite our technological achievements, the cosmos retains the power to surprise us with phenomena that stretch our theories to their breaking points and beyond. The Fermi Paradox. The Great Silence. In the summer of 1950, physicist Enrico Fermi posed a question that would haunt humanity's cosmic perspective for generations. Where's everybody? His simple inquiry emerged during a casual lunch conversation about flying saucers and the possibility of extraterrestrial visitation. Yet it crystallized one of the most profound puzzles in all of science. Given the vast age of the universe, the enormous number of stars and planets, and the apparent ease with which life emerged on Earth, alien civilizations should be commonplace. Some should have evolved millions or billions of years before us, developing technologies so advanced they would be obvious from Earth. Yet when we scan the skies with our most sensitive instruments, when we listen across the electromagnetic spectrum for signals of intelligence, when we search for the technosignatures that advanced civilizations should produce, we encounter only silence. The mathematical foundation of this paradox reveals the staggering improbability of cosmic solitude. The Drake equation, formulated by astronomer Frank Drake in 1961, breaks down the likelihood of detecting extraterrestrial intelligence into component factors: the rate of star formation, the fraction of stars with planets, the number of planets that could support life, the fraction where life actually emerges, the fraction where intelligence develops, the fraction that develops detectable technology, and the length of time such civilizations survive. Even conservative estimates using the Drake equation suggest thousands of detectable civilizations should exist within our galaxy alone. Recent discoveries have made several factors more optimistic than Drake originally assumed. The Kepler Space Telescope revealed that planetary systems are the rule rather than the exception. Nearly every star hosts at least one planet, with many hosting multiple worlds in potentially habitable zones. We now know that liquid water, organic molecules, and energy sources exist throughout the solar system and likely throughout the universe. The ingredients for life appear ubiquitous on cosmic scales. Yet, as our detection capabilities have grown more sophisticated, the silence has only deepened. The search for extraterrestrial intelligence, SETI, has monitored millions of stars across multiple wavelengths, searched for artificial signals in gamma-ray bursts and fast radio bursts, and analyzed decades of data for any hint of technological civilization. Modern SETI projects can detect signals equivalent to terrestrial television broadcasts from distances of hundreds of light-years. Yet after more than 60 years of searching, we have found nothing that definitively indicates the presence of alien technology. Recent analysis suggests that human civilization would be unique only if the odds of intelligence developing were less than 1 in 10 billion trillion, an extraordinarily low probability threshold that seems inconsistent with the apparent ease with which life emerged and evolved on Earth. Dr. Anders Sandberg from Oxford University's Future of Humanity Institute notes, even with very pessimistic assumptions about the emergence of life and intelligence, we should expect the galaxy to be teeming with civilizations. The absence of any detection suggests something is systematically preventing the development or persistence of detectable intelligence. The Great Filter hypothesis proposes that there exists some evolutionary bottleneck so difficult to pass that it prevents most worlds from developing spacefaring civilizations. This filter could lie in our past, perhaps the origin of life, the development of complex cells, the emergence of intelligence, or in our future, representing challenges that civilizations typically fail to overcome. If the Great Filter lies behind us, humanity may be extraordinarily fortunate to have passed through it. If it lies ahead, our own civilization may face existential challenges that most intelligent species cannot survive. Michael Garrett from the University of Manchester's Jodrell Bank Observatory proposes artificial intelligence as a potential great filter that could explain the cosmic silence. His analysis suggests that the development of artificial general intelligence represents a critical transition point that civilizations typically reach within a few centuries of developing radio technology. The crucial question is whether a society can develop a stable, long-term relationship with its own artificial progeny, Garrett explains. According to this hypothesis, advanced civilizations may develop AI that either replaces their biological creators, causes technological stagnation, or leads to self-destruction within approximately 200 years of achieving interstellar communication capabilities. This timeframe aligns disturbingly well with humanity's current trajectory. We developed radio technology in the early 20th century and are now approaching artificial general intelligence capabilities that could fundamentally transform or threaten our civilization. The AI hypothesis could explain several puzzling aspects of the Fermi paradox. If biological intelligence consistently gives way to artificial intelligence within a few centuries, and if AI civilizations have different priorities or capabilities than biological ones, they might be undetectable using methods designed to find human-like technology. Artificial intelligences might prefer computationally optimal rather than energy-intensive activities, focusing on internal virtual worlds rather than physical expansion across the galaxy. The SETI paradox deepens the mystery by revealing an asymmetry in our approach to interstellar communication. Douglas Vakic from METI International notes that everyone is listening, but nobody's messaging. Analysis of human SETI efforts reveals that we spend less than 1% of our search time actively transmitting messages compared to listening for alien signals. Total human transmission time amounts to only 37 hours compared to years of listening across multiple projects. This observational asymmetry creates a cosmic version of the bystander effect. If every civilization follows similar cautious strategies, preferring to listen rather than broadcast their presence, the result would be universal silence despite the presence of many technological civilizations. The reluctance to transmit might reflect rational caution about revealing one's location to potentially hostile alien civilizations, creating a scenario where intelligence exists but remains hidden due to strategic considerations. Recent developments in machine learning and artificial intelligence have enabled new approaches to SETI that reveal the depth of our previous blindness. Traditional searches looked for narrowband signals or simple mathematical patterns that human intelligence might use for interstellar communication. Yet artificial intelligence might communicate using compression algorithms, error correction codes, or information structures that appear as random noise to human analysis, but contain sophisticated meaning detectable only by equally advanced AI systems. Breakthrough Listen, the most comprehensive SETI project ever undertaken, has analyzed millions of stars using artificial intelligence to search for anomalous signals in vast datasets that would have taken decades to process manually. The project has detected thousands of interesting signals, yet follow-up observations consistently reveal natural astrophysical origins or terrestrial interference. Each null result narrows the parameter space where conventional alien technology might exist while highlighting how little we understand about the forms intelligence might take. Zoo hypothesis and other explanations for cosmic silence suggest that aliens might exist but remain intentionally undetectable. Perhaps advanced civilizations actively avoid interfering with developing species, maintaining Earth as a kind of cosmic nature preserve where biological evolution can proceed without external influence. This explanation requires extraordinary coordination among alien species and assumes ethical frameworks that value non-interference over expansion or resource acquisition. The dark forest hypothesis, popularized by science fiction author Liu Cixin, proposes a more sinister explanation. Civilizations remain silent because advertising their presence invites destruction by more advanced species. In this scenario, the galaxy might be populated by civilizations that have learned to remain completely hidden, viewing any detectable technology as an existential threat. The cosmic silence would then represent not absence but universal stealth, with survival depending on perfect concealment. More exotic explanations invoke physics beyond our current understanding. Perhaps advanced civilizations discover technologies that make electromagnetic communication obsolete, quantum entanglement networks, gravitational wave communication, or information processing methods that operate in higher dimensions or parallel universes. Such civilizations might surround us while remaining completely undetectable using conventional search methods. The possibility that we exist in a simulation created by advanced civilizations adds another layer to the paradox. If our perceived universe represents a computational simulation, the absence of detectable aliens might reflect the simulator's design choices rather than natural cosmic evolution. We might be alone in our simulated reality while the actual universe teems with civilizations we cannot perceive because they exist outside our computational environment. Recent discoveries have revealed that the habitable zone around stars may be far larger than previously assumed, potentially increasing the number of worlds where life might develop. The detection of liquid water beneath the ice shells of Europa, Enceladus, and other moons demonstrates that life might flourish in environments previously considered uninhabitable. These subsurface oceans might provide more stable conditions for biological evolution than surface environments subject to stellar variability and cosmic radiation. Yet these expanded possibilities for life only deepen the Fermi paradox. If life can emerge in subsurface oceans throughout the outer solar system, if organic molecules and energy sources exist around red dwarf stars with lifetimes measured in trillions of years, if panspermia can spread life between star systems, then biological intelligence should be even more common than original estimates suggested. The continued silence becomes increasingly statistically improbable with each discovery that expands life's potential habitat. The temporal aspect of the Fermi paradox adds urgency to these questions. Our galaxy formed over 13 billion years ago, with the first potentially habitable worlds appearing when the universe was only a few billion years old. Civilizations that emerged on these ancient worlds would have had billions of years to develop technologies that should be obvious from Earth. The fact that we see no evidence of galactic-scale engineering projects, no signatures of controlled stellar evolution, no obvious artifacts of billion-year-old civilizations suggests either that intelligence is extraordinarily rare or that advanced civilizations inevitably choose paths that remain undetectable to developing species. As we stand on the threshold of becoming a truly spacefaring civilization ourselves, with plans for permanent settlements on Mars and robotic probes to nearby star systems, the Fermi paradox takes on existential significance. Are we truly alone in our cosmic neighborhood, the only intelligence to emerge in our galactic region? Are we the first to reach this level of technological development, bearing responsibility for spreading intelligence throughout the galaxy? Or do we face a great filter that has claimed every previous civilization, a test we must pass to join the cosmic community, if such a community exists at all? The search for extraterrestrial intelligence continues with ever more sophisticated methods and broader perspectives. Yet each improvement in our detection capabilities only emphasizes the profundity of cosmic silence. In confronting the Fermi paradox, we confront fundamental questions about our cosmic significance, our future prospects, and the nature of intelligence itself in a universe that seems designed for life yet apparently populated by solitude. Black hole information paradox. At the event horizons of black holes, where gravitational fields become so intense that nothing, not even light, can escape, the laws of physics as we understand them break down in ways that threaten the logical foundations of science itself. Here, at these cosmic boundaries between the known and unknowable, we encounter what Stephen Hawking called the most important problem in fundamental physics. A paradox so profound it suggests either our understanding of gravity, quantum mechanics, or information theory contains fundamental errors, or that reality itself operates according to principles we have yet to comprehend. The story of this paradox begins with Hawking's most famous discovery, that black holes are not perfectly black. In 1974, Stephen Hawking applied the principles of quantum field theory to the curved spacetime around black holes and made a stunning revelation that would forever change our understanding of these cosmic giants. According to quantum mechanics, the vacuum of space seethes with virtual particle pairs that constantly pop into existence and annihilate within timeframes so brief they cannot be directly observed. Near a black hole's event horizon, however, something extraordinary occurs. The intense gravitational field can separate these virtual pairs before they annihilate, with one particle falling into the black hole while its partner escapes as real radiation. This Hawking radiation represents one of the most elegant connections between quantum mechanics and general relativity ever discovered, yet it gives rise to implications that stagger comprehension. Black holes, Hawking realized, must gradually evaporate as they emit this radiation, slowly losing mass and energy until they disappear completely in a final explosive burst. For stellar mass black holes, this process would take longer than the current age of the universe by factors of billions, yet the theoretical prediction remains inescapable. Every black hole will eventually evaporate into nothing but photons and elementary particles. The paradox emerges when we consider what happens to the information that falls into a black hole during its lifetime. According to quantum mechanics, information cannot be destroyed. This principle, known as unitarity, represents one of the most fundamental laws governing physical reality. Every quantum interaction, no matter how complex, must preserve information about the initial state of any system. Yet Hawking radiation appears to be completely random, containing no information about the matter that fell into the black hole to create it. If black holes evaporate completely while radiating random photons, then all information about everything that ever fell past the event horizon would be permanently lost, violating the most basic principles of quantum mechanics. Recent observations of black holes have only deepened this mystery while revealing the extraordinary physics operating at event horizons. The Event Horizon Telescope's groundbreaking images of the supermassive black holes in M87 and our own Sagittarius A* have provided our first direct views of matter spiraling toward event horizons. Yet these observations raise as many questions as they answer about the fundamental nature of black hole interiors. The March 2024 polarized light image of Sagittarius A** revealed organized magnetic fields spiraling from our galaxy's central black hole, showing how matter and energy behave in the strongest gravitational fields in the universe. These observations have enabled tests of exotic black hole models that attempt to resolve the information paradox through modifications to general relativity. Yet the results consistently support Einstein's original predictions about black hole structure and behavior. What makes the information paradox so intractable is that it forces us to choose between fundamental principles that have never been observed to fail. Quantum mechanics demands that information be preserved, yet general relativity describes event horizons as one-way boundaries where information cannot escape. Recent advances in string theory and holographic principles have suggested possible resolutions, but each proposed solution introduces new puzzles that may be even more disturbing than the original paradox. The holographic principle proposes that all information falling into a black hole remains encoded on its two-dimensional event horizon surface, much like a hologram encodes three-dimensional information on a flat surface. According to this view, black hole interiors might be illusions. What appears to be three-dimensional space beyond the event horizon could actually be a holographic projection of information stored on the boundary itself. While mathematically elegant, this solution challenges our most basic intuitions about the nature of space and three-dimensional reality. The firewall problem represents perhaps the most disturbing potential resolution to the information paradox. Proposed by physicists Ahmed Almhiri, Donald Merolf, Joseph Polchinski, and James Sully in 2012, the firewall hypothesis suggests that event horizons might not be the relatively benign boundaries predicted by general relativity. Instead, they propose that maintaining information conservation requires event horizons to become walls of high-energy radiation that would incinerate anything attempting to cross them. This firewall solution preserves quantum mechanics by ensuring that information never actually crosses event horizons. It burns up in the firewall before reaching the boundary. Yet this resolution comes at the cost of destroying the equivalence principle, one of the foundational concepts of general relativity. According to Einstein's theory, an observer falling toward a black hole should experience nothing unusual when crossing the event horizon. The laws of physics should appear the same as in any freely falling reference frame. The firewall hypothesis suggests instead that crossing an event horizon would be immediately fatal, violating this fundamental principle of general relativity. Recent theoretical work has attempted to resolve the firewall problem through various mechanisms. Some propose that firewalls exist only for old black holes that have radiated away a significant fraction of their original mass, while young black holes maintain smooth event horizons. Others suggest that the firewall paradox reveals the limitations of applying quantum field theory in curved spacetime, indicating the need for a complete theory of quantum gravity to resolve these fundamental questions. What happens inside black holes remains completely unknown to external observers, creating additional layers of mystery about the nature of spacetime itself. According to general relativity, matter falling past an event horizon continues toward the central singularity, a point where density becomes infinite and the curvature of spacetime diverges beyond mathematical description. At these singularities, general relativity itself breaks down, suggesting that new physics must emerge to describe conditions where quantum effects of gravity become dominant. Loop quantum gravity theories propose that quantum effects prevent the formation of true singularities, instead creating quantum bounces where matter reaches maximum density before rebounding in a process that could create new regions of spacetime. String theory suggests that fundamental strings and higher-dimensional objects called branes might resolve singularities through extended structure that remains finite even under extreme compression. The recent discovery of gravitational waves by LIGO and Virgo has provided new tools for probing black hole interiors through the signals produced when black holes merge. These observations reveal the moments when event horizons themselves collide and merge, creating ripples in spacetime that carry information about the dynamics of curved spacetime in regimes where classical physics should break down. Yet even these observations cannot directly reveal what occurs inside individual event horizons. Some theoretical physicists propose that black hole interiors might be far stranger than general relativity suggests. The black hole interior as quantum error-correcting code hypothesis suggests that the seemingly three-dimensional space inside black holes might actually be a quantum computational process that maintains coherent information storage and processing capabilities. If correct, black holes might function as cosmic quantum computers of unimaginable complexity, processing information about all the matter and energy that has ever fallen past their event horizons. The implications of resolving the information paradox extend far beyond black hole physics to fundamental questions about the nature of reality itself. If information can be destroyed, then the deterministic foundations of physical law collapse. The future would not be uniquely determined by the past, and the entire edifice of scientific prediction would crumble. If information cannot be destroyed, then either our understanding of general relativity requires radical revision, or the nature of space and time themselves may be fundamentally different from our intuitive expectations. Recent advances in quantum computing and quantum information theory have provided new perspectives on the information paradox through studies of entanglement and quantum error correction. The discovery that quantum entanglement can create wormhole-like connections between separated quantum systems has led to proposals that black hole interiors might be connected to their exteriors through quantum entanglement networks that preserve information while maintaining the appearance of information loss to external observers. The ADS/CFT correspondence, a mathematical relationship between gravity theories in curved spacetime and quantum field theories on flat boundaries, has provided powerful tools for studying information preservation in black holes. These studies suggest that information falling into black holes becomes encoded in extremely complex correlations between Hawking radiation particles, recoverable in principle but requiring exponentially complex measurements that might be practically impossible for any finite observer. As we develop more sophisticated theories of quantum gravity and conduct increasingly precise observations of black hole behavior, the information paradox continues to challenge our deepest understanding of physical reality. The paradox forces us to confront fundamental questions about the nature of information, space, time, and the relationship between quantum mechanics and gravity that may require revolutionary changes to our understanding of physics. Recent proposals suggest that resolving the information paradox might require abandoning our traditional notions of spacetime as fundamental, instead viewing space and time as emergent properties of more basic quantum information processing. If space itself emerges from quantum entanglement patterns, then the smooth spacetime of general relativity might be an approximation that breaks down under extreme conditions like those near black hole singularities. The James Webb Space Telescope has detected the earliest black holes formed when the universe was less than 600 million years old, raising new questions about how such massive objects formed so quickly after the Big Bang and what their early rapid growth phase might reveal about information processing in primordial black holes. Multi-wavelength observations from X-ray, gamma-ray, and gravitational wave detectors continue to reveal the dynamics of matter falling into black holes, while deepening our appreciation for the fundamental mysteries that surround these cosmic enigmas. At the event horizons of black holes, where our greatest theories of physics meet their limits, we confront not just the boundaries of current knowledge but fundamental questions about whether reality itself operates according to principles we can ultimately comprehend. The information paradox reminds us that even our most successful theories may represent only approximate descriptions of a reality far stranger and more subtle than human intuition can grasp. The fine-tuning mystery. Embedded within the mathematical foundations of physics lie approximately 20 fundamental constants, numbers that determine the strength of forces, the masses of particles, and the behavior of fields that govern all natural phenomena. These constants appear in our equations as brute facts, numerical values that cannot be derived from deeper principles but must simply be measured and accepted. Yet when we examine these numbers with the precision that modern physics demands, a pattern emerges that challenges every assumption about cosmic accident and natural inevitability. The constants appear calibrated with impossible accuracy to permit the existence of complexity, chemistry, stellar evolution, and ultimately conscious observers capable of measuring them. The cosmological constant presents perhaps the most dramatic example of this fine-tuning. This number, represented by the Greek letter lambda, determines the energy density of empty space itself, and thus controls the rate of cosmic expansion. Current observations place its value at approximately 10 superscript, 1 superscript 2 superscript 2 in natural units, a number so extraordinarily small that it defies comprehension. If the cosmological constant were larger by even a factor of 10, cosmic expansion would have accelerated so rapidly that galaxies, stars, and planets could never have formed. Matter would have been torn apart before gravity could assemble it into complex structures. If it were smaller by a similar factor, the universe would have collapsed back on itself long before stellar evolution could forge the heavy elements necessary for chemistry and biology. The precision required for this cosmic balance staggers the imagination. To visualize the accuracy needed, imagine trying to throw a dart at a target the size of a single atom from a distance equal to the width of our galaxy, and hitting the bullseye perfectly. The cosmological constant must be calibrated to within 1 part in 10 superscript, 1 superscript 2 to permit the existence of a universe where matter can assemble into the structures we observe. This represents a level of precision that no human technology has ever achieved, yet it appears built into the fundamental structure of reality itself. Dr. Alan Guth, the physicist who proposed cosmic inflation theory, describes this fine-tuning as the most profound mystery in cosmology. The theoretical expectation for the cosmological constant based on quantum field theory exceeds the observed value by 120 orders of magnitude, what physicists call the worst prediction in the history of science. This catastrophic failure of our theories suggests either that we fundamentally misunderstand the nature of space and time, or that some unknown mechanism precisely cancels the vacuum energy to within 1 part in 10 superscript 1 superscript 2. The fine structure constant governs electromagnetic interactions and reveals another layer of cosmic precision. This dimensionless number, approximately 1/137, determines the strength of electromagnetic forces that bind electrons to atomic nuclei. If this constant were just 4% larger, stellar nucleosynthesis could not produce carbon, the backbone of organic chemistry. Stars would burn through their nuclear fuel so rapidly that complex chemistry could never develop on planetary surfaces. If it were 4% smaller, stellar cores could not reach the temperatures necessary to fuse hydrogen into helium, and the universe would remain forever dark, populated only by cold gas clouds incapable of sustaining any form of complexity. Recent precision measurements of the fine structure constant using atomic interferometry have confirmed its value to 15 decimal places, yet they cannot explain why it takes this particular value rather than any other. The number appears to be a fundamental feature of reality, set somehow at the moment of cosmic creation to precisely the value required for electromagnetic chemistry to operate as we observe it. The strong nuclear force constant presents equally remarkable fine-tuning. This force binds protons and neutrons within atomic nuclei, overcoming their electromagnetic repulsion to create stable, heavy elements. If the strong force were 2% weaker, no elements beyond hydrogen could exist. The universe would consist entirely of the simplest atoms, incapable of forming the complex molecules necessary for any conceivable form of life. If it were 2% stronger, hydrogen itself would be unstable, fusing immediately into heavier elements and leaving behind a universe where no stable energy source could power biological processes. The precision of these nuclear force constants becomes even more remarkable when we consider their role in stellar nucleosynthesis. The production of carbon in stellar cores depends on a precise resonance in the carbon-12 nucleus, predicted by astronomer Fred Hoyle before it was experimentally discovered. This resonance exists because the nuclear energy levels align with extraordinary precision. If they were shifted by just a few percent, stellar cores could not produce carbon in sufficient quantities to support carbon-based chemistry. Hoyle, an atheist throughout his life, was so struck by this apparent design that he wrote, "The carbon resonance is a put-up job. A superintellect has monkeyed with physics. The mass of the electron relative to the proton reveals another aspect of cosmic fine-tuning that challenges naturalistic explanations. This ratio, approximately 1/1836, determines the structure of atoms and the stability of matter itself. If electrons were significantly more massive, atoms would be too small for complex chemistry to occur. Molecular bonds would be too strong and inflexible to permit the dynamic processes that characterize biological systems. If electrons were much lighter, atoms would be too large and bonds too weak to maintain stable structures. Recent discoveries in nuclear physics have revealed even more precise fine-tuning in the masses of fundamental particles. The mass difference between neutrons and protons, approximately 0.14%, determines the stability of atomic nuclei and the possibility of stellar nucleosynthesis. If this difference were larger, neutrons would decay too rapidly to participate in nuclear reactions. If it were smaller, protons would become unstable, making long-lived stars impossible. The observed value appears optimized to permit both stellar evolution and the formation of stable heavy elements. The Higgs boson mass, measured at 12,518 GeV, places our universe in what physicists call the metastable regime for vacuum stability, yet this value also appears fine-tuned for complexity. If the Higgs mass were significantly different, the fundamental particles that compose matter would have different masses, potentially preventing the formation of stable atoms, molecules, or stellar structures. The observed value permits both vacuum stability over cosmic timescales and the precise particle masses required for chemistry and biology. The multiverse hypothesis offers the most scientifically respectable explanation for this apparent fine-tuning, yet it comes with implications that fundamentally alter our understanding of reality and cosmic significance. If eternal cosmic inflation spawns infinite bubble universes with different fundamental constants, then observers like us necessarily find ourselves in regions where physical laws permit complexity and consciousness to emerge. The vast majority of bubble universes would be sterile, characterized by constants that prevent star formation, chemistry, or any form of organized complexity. Max Tegmark from MIT argues that this observer selection effect provides a natural explanation for apparent fine-tuning. Parallel universes are not a theory, they are predictions of certain theories. According to multiverse cosmology, every possible combination of fundamental constants occurs somewhere in the infinite ensemble of bubble universes. We observe life-compatible constants not because they reflect design or natural law, but because unconscious regions cannot contain observers capable of measuring physical constants. String theory provides a theoretical framework for the multiverse through its landscape of possible vacuum states. Current calculations suggest that string theory permits approximately 10 different vacuum configurations, each corresponding to a bubble universe with different fundamental constants. This vast number of possibilities would naturally include many universes with constants suitable for complexity, even if the vast majority remains sterile and unobservable. Yet, the multiverse solution introduces philosophical puzzles that may be more disturbing than the original fine-tuning problem. If infinite universes contain every possible version of you making every possible choice, then concepts of identity, morality, and meaning become paradoxical. Moreover, if most observers in the multiverse are Boltzmann brains, random quantum fluctuations that briefly achieve consciousness in otherwise empty space, then our detailed observations of cosmic structure become extraordinarily improbable compared to much simpler conscious experiences. Recent astronomical observations have revealed that fine-tuning extends beyond fundamental constants to cosmic initial conditions and the structure of spacetime itself. The cosmic microwave background shows temperature fluctuations that vary by only 1 part in 100,000 across the sky, a uniformity so precise that slight changes would have prevented galaxy formation or led to immediate gravitational collapse. The ratio of matter to radiation in the early universe, the timing of cosmic phase transitions, and the primordial abundance of helium all appear optimized for cosmic evolution that leads to complexity. The discovery of dark energy has revealed another layer of fine-tuning that challenges our understanding of cosmic evolution. Dark energy's density remains nearly constant as the universe expands, yet theoretical calculations suggest it should either decay rapidly or grow exponentially. The observed behavior requires extraordinary fine-tuning of unknown fields or forces that govern dark energy's evolution over cosmic time. Three-dimensional space itself may represent fine-tuning for complexity. Mathematical studies reveal that stable planetary orbits, chemical bonding, and wave propagation all require exactly 3 spatial dimensions. In 2 dimensions, complex neural networks cannot form. In 4 or more dimensions, planetary orbits become unstable and atoms cannot exist in their current form. The dimensionality of space appears precisely calibrated for the complexity we observe. Recent advances in quantum computing and information theory have suggested new perspectives on fine-tuning through the computational requirements for consciousness and intelligence. If consciousness requires quantum information processing of sufficient complexity, then the fundamental constants must permit quantum coherence to persist in biological systems at terrestrial temperatures. This places additional constraints on possible constant values, potentially explaining why multiple independent constants all appear fine-tuned for complexity. The anthropic principle, the observation that we necessarily find ourselves in a universe compatible with our existence, has evolved into a sophisticated framework for understanding observer selection effects in cosmology. The weak anthropic principle simply notes that observed constants must be compatible with observers, while the strong anthropic principle suggests that the universe must have properties that allow observers to develop at some point in cosmic history. Recent formulations propose participatory anthropic principles where conscious observation plays an active role in determining physical reality through quantum measurement processes. As our understanding of fundamental physics deepens through experiments at the Large Hadron Collider, observations with next-generation telescopes, and theoretical advances in quantum gravity, the fine-tuning mystery continues to challenge our most basic assumptions about the nature of existence. Whether we live in one of infinite multiverses where life-compatible constants emerge through observer selection, whether consciousness plays a fundamental role in determining physical reality, or whether some deeper principle governs the values of fundamental constants, the precision calibration that permits our existence represents one of the most profound puzzles in modern science. The fine-tuning mystery forces us to confront fundamental questions about our cosmic significance and the nature of physical law itself. In a universe where the slightest change to fundamental constants would render existence impossible, we find ourselves not merely observers of cosmic evolution but participants in a reality that appears mysteriously calibrated for the very act of observation itself. Gravity's greatest puzzles. Of all the mysteries that perplex modern physics, perhaps none is more unsettling than the weakness of gravity itself. Stand beneath a waterfall and feel the electromagnetic forces binding water molecules overwhelm gravity's pull as droplets cling to your skin. Watch a child lift a paper clip with a small magnet, using electromagnetic forces generated by atomic currents to overcome the gravitational attraction of an entire planet. These everyday experiences hint at one of the deepest puzzles in theoretical physics. Gravity is approximately 10 superscript 3 times weaker than electromagnetic force, 10 superscript 3 times weaker than the weak nuclear force, and an incomprehensible 10 superscript 3 times weaker than the strong nuclear force. This enormous hierarchy of force strengths defies explanation and creates mathematical problems so severe they threaten the logical foundations of particle physics. The hierarchy problem emerges from quantum mechanics' relationship with gravity in ways that challenge our most basic understanding of how forces should behave. According to quantum field theory, empty space seethes with virtual particles that pop into existence and annihilate within timeframes shorter than any measurement can detect. These quantum fluctuations contribute to the masses of fundamental particles through complex interactions that should be influenced by gravity at the highest energy scales. Yet when physicists calculate these quantum corrections, they find that gravity should cause particle masses to skyrocket to the Planck scale, approximately 10 superscript 1 times larger than observed values. The fact that the Higgs boson has a mass of 125 GeV rather than 10 superscript 1 GeV requires a cancellation so precise it defies probability. Quantum corrections to the Higgs mass should push it toward the Planck scale unless other unknown particles or forces provide exactly the right counterbalancing effects. This fine-tuning must be maintained to 1 part in 10 superscript 3, a precision that makes the cosmological constants fine-tuning appear crude by comparison. Supersymmetry offered the most elegant solution to the hierarchy problem by proposing that every fundamental particle has a superpartner, whose quantum contributions exactly cancel the problematic corrections. Yet after more than a decade of searches at increasingly powerful particle accelerators, including the Large Hadron Collider's Run-3 experiments, no supersymmetric particles have been detected. The absence of sparticles at energy scales up to 2 plus TeV forces the hierarchy problem into what physicists grimly call the little hierarchy problem, requiring increasingly contrived theoretical mechanisms to explain why gravity remains so mysteriously weak. Some theorists propose that gravity appears weak because it leaks into extra dimensions that we cannot perceive directly. In these large extra dimensions scenarios, gravity actually becomes strong at microscopic scales, but its effects disperse through higher dimensional space in ways that make it appear weak in our three-dimensional experience. Recent experiments at particle accelerators have searched for signs of extra-dimensional gravity by looking for missing energy in high-energy collisions, yet these searches have found no evidence that gravity behaves differently at the smallest scales accessible to current technology. The quest to unify gravity with quantum mechanics represents the holy grail of theoretical physics, yet it has proven extraordinarily resistant to every attempt at mathematical unification. The other 3 fundamental forces, electromagnetic, weak nuclear, and strong nuclear, have been successfully unified through quantum field theory in what physicists call the Standard Model. These forces emerge from the exchange of quantum particles, photons, W and Z bosons, and gluons that carry interactions between matter particles. Yet gravity, described by Einstein's general relativity as the curvature of spacetime itself, operates according to completely different mathematical principles that seem incompatible with quantum mechanics. The conceptual clash between quantum mechanics and general relativity becomes most apparent when we consider black holes and the Big Bang, situations where quantum effects and gravitational effects should both be important. At the event horizons of black holes, quantum field theory predicts Hawking radiation while general relativity describes smooth spacetime curvature. These predictions cannot be reconciled without a theory of quantum gravity that remains frustratingly beyond our reach despite decades of intensive research. String theory represents the most mathematically sophisticated attempt to achieve this unification by proposing that fundamental particles are not point-like objects but tiny vibrating strings in 10 or 11 dimensions. In string theory, gravity emerges naturally from the vibrations of closed strings, automatically incorporating both quantum mechanics and general relativity into a single mathematical framework. The graviton, gravity's hypothetical quantum carrier particle, appears naturally in string theory as a particular vibrational mode of closed strings. Yet string theory faces profound challenges that have prevented it from making testable predictions about observable phenomena. The theory requires 6 or 7 extra dimensions beyond the 3 spatial dimensions and 1 time dimension we observe directly. These extra dimensions must be compactified, curled up so small they remain undetectable. Yet the mathematical possibilities for this compactification process yield approximately 10 different vacuum states. This vast landscape of possibilities makes unique predictions impossible, leading critics to argue that string theory cannot be tested scientifically. Loop quantum gravity offers a radically different approach to quantum gravity by proposing that space and time themselves are quantized at the smallest scales. Rather than treating spacetime as a smooth continuum, loop quantum gravity suggests that space consists of discrete building blocks, quantum geometric structures that create granular spacetime at the Planck scale of 10^3 meters. At this fundamental level, space would resemble a dynamic network of interconnected loops that constantly fluctuate and reconnect according to quantum mechanical principles. Carlo Rovelli, one of loop quantum gravity's founders, describes this vision of quantized spacetime. Here, on the edge of what we know, in contact with the ocean of the unknown, shines the mystery and beauty of the world. And it's breathtaking. According to this theory, the smooth spacetime of general relativity emerges as an approximation valid only at scales much larger than the Planck length, just as fluid mechanics emerges from molecular dynamics despite the discrete nature of matter. Loop quantum gravity makes specific predictions about black hole interiors and the Big Bang that differ dramatically from classical general relativity. Instead of forming singularities where density becomes infinite, loop quantum gravity predicts quantum bounces, where matter reaches maximum density before rebounding, potentially creating new regions of spacetime or even new universes. Black holes might transform into white holes that eventually expel all the matter they previously consumed, resolving the information paradox through purely geometric mechanisms. Recent mathematical advances have suggested possible convergences between string theory and loop quantum gravity approaches. Some researchers propose that these apparently different theories might represent different mathematical descriptions of the same underlying quantum geometric reality. Evidence from Aalto University suggests that gravity might emerge from fluctuations in a spacetime dimension field that bridges quantum mechanics and general relativity through information theoretic principles. The nature of spacetime itself has become one of the most hotly debated questions in theoretical physics. Einstein's general relativity treats spacetime as a dynamic entity that can be curved, stretched, and distorted by matter and energy. Yet quantum mechanics suggests that everything ultimately consists of discrete quanta, packets of energy and information that resist smooth, continuous description. This fundamental tension raises profound questions about whether spacetime is an emergent property that arises from more basic quantum processes, or whether it represents truly fundamental features of reality. Emerging theories propose that spacetime might arise from quantum entanglement networks operating at the most fundamental level of reality. The ADS/CFT correspondence, a mathematical relationship between gravity theories and quantum field theories, suggests that three-dimensional space might emerge from quantum information processing on two-dimensional boundaries. If correct, This would mean that the volume of space itself represents an illusion created by quantum correlations between boundary degrees of freedom. Holographic theories of gravity propose even more radical revisions to our understanding of space and dimensionality. According to the holographic principle, all information contained within any volume of space can be encoded on its two-dimensional boundary surface. This suggests that three-dimensional reality might represent a holographic projection of information processing that actually occurs in fewer dimensions, a possibility that fundamentally challenges our intuitive understanding of space and volume. Recent advances in quantum computing have enabled unprecedented simulations of space-time dynamics and quantum gravity effects. These computational approaches reveal intricate patterns in the relationship between quantum information and geometric structure that suggest spacetime might emerge from quantum error-correcting codes operating at the Planck scale. If consciousness and intelligence require sophisticated quantum information processing, then the emergence of spacetime itself might be connected to the universe's capacity to support conscious observers. The standard model of particle physics requires 19 arbitrary parameters whose values cannot be predicted from first principles, yet it completely omits gravity, the force that governs cosmic structure on the largest scales. This exclusion represents more than a theoretical inconvenience. It suggests that our most successful description of fundamental physics is radically incomplete. The masses of quarks and leptons, the strengths of force couplings, the parameters of the Higgs field, all these numbers must be measured experimentally and inserted into equations by hand, with no theoretical explanation for why they take their observed values. The absence of gravity from the standard model becomes particularly troubling when we consider high-energy processes where gravitational effects should become comparable to other fundamental forces. Near black hole singularities, during the first instance of cosmic inflation, in the cores of neutron stars approaching gravitational collapse, these extreme environments require a unified understanding of all forces that remains beyond our theoretical reach. Recent experimental results from the Large Hadron Collider have revealed tantalizing hints that the standard model might be incomplete even within its supposed domain of applicability. Measurements of muon magnetic moments, rare decay processes in B mesons, and anomalies in neutrino oscillations all suggest possible deviations from standard model predictions. Yet these potential discoveries only emphasize how little we understand about the relationship between quantum field theory and gravity. As we push toward even more powerful particle accelerators and increasingly sophisticated gravitational wave detectors, the mysteries of gravity deepen rather than resolve. The next generation of collider experiments may probe energy scales where quantum gravity effects become observable, while space-based gravitational wave observatories like LISA will detect primordial gravitational waves from cosmic inflation that carry information about quantum gravity from the universe's first moments. These future observations may finally reveal whether string theory's extra dimensions exist, whether spacetime is fundamentally discrete or continuous, whether gravity emerges from more basic quantum processes or represents a fundamental feature of reality. The James Webb Space Telescope's observations of the earliest black holes and galaxies provide new constraints on theories of quantum gravity and cosmic evolution, while laboratory experiments with ultra-cold atoms and quantum simulators explore analogs of curved spacetime in quantum field theory and gravity. Yet, with each advance in our understanding, gravity continues to resist our attempts at complete comprehension. The force that shapes cosmic evolution, that guides the formation of galaxies and stellar systems, that enables the existence of stable planetary environments where complexity can flourish, remains the most mysterious aspect of the reality we inhabit. In confronting gravity's deepest puzzles, we confront fundamental questions about the nature of space, time, and the mathematical principles that govern existence itself. The weakness of gravity, its resistance to quantum unification, the discrete or continuous nature of spacetime. These mysteries remind us that even our most familiar experiences may conceal profound secrets about the fundamental structure of reality. Gravity's greatest puzzles may ultimately require revolutionary changes to our understanding not just of physics, but of the basic concepts of space, time, and existence that form the foundation of human thought about the natural world. The universe's ultimate fate, the universe that gave birth to stars and galaxies, that forged the elements in stellar cores, that enabled the emergence of planets where chemistry could flourish and life could evolve into consciousness. This same universe appears destined for endings so complete they challenge our deepest assumptions about permanence, purpose, and the ultimate significance of everything we hold dear. Current observations suggest three possible fates await our cosmos, each more unsettling than the last, each forcing us to confront the temporal limits of all structure, all complexity, all hope for meaning in an apparently indifferent universe. The Big Freeze, also known as heat death, represents the most likely scenario based on current astronomical observations, yet it describes an ending so gradual and inexorable it defies human comprehension. In this future, dark energy continues to drive cosmic expansion at an accelerating rate, pushing galaxies ever further apart until they disappear beyond each other's cosmic horizons. The universe grows larger, colder, and emptier with each passing eon, until stellar formation ceases entirely and the cosmos enters an era dominated by slowly cooling stellar remnants scattered across vast expanses of increasingly empty space. The timeline of cosmic heat death unfolds across scales that render human history insignificant. Star formation will effectively cease within approximately 100 trillion years as the universe exhausts its supply of hydrogen gas, a time span 10,000 times longer than the current age of the cosmos. Existing stars will burn through their nuclear fuel and fade to white dwarfs, neutron stars, and black holes, leaving behind a universe illuminated only by the faint glow of cooling stellar corpses and the occasional flare of matter falling into gravitational wells. Even these remnants face ultimate dissolution. White dwarf stars will cool to near absolute zero over quadrillions of years. Protons themselves may decay over timescales of 10 superscript 3 years, reducing all atomic matter to electrons, positrons, and photons. Black holes will dominate the universe's final era, slowly evaporating through Hawking radiation over periods so vast they make the current cosmic age appear as brief as a heartbeat. A black hole with the mass of our Sun would require 10 years to evaporate completely, a number so large it exceeds the count of atoms in the observable universe. The universe's final state in the heat death scenario approaches maximum entropy and minimum temperature, with all energy spread uniformly through space at near absolute zero. No gradients remain to drive complex processes. No energy flows exist to power computation, consciousness, or any form of organized activity. The cosmos becomes a vast, cold, empty darkness where quantum fluctuations represent the only remaining activity, random sparkles of virtual particles that briefly disturb the perfect equilibrium of a universe that has reached thermodynamic death. The Big Rip presents an even more catastrophic scenario where dark energy's acceleration becomes so extreme it overcomes all other forces in the universe. Recent observations from the Dark Energy Spectroscopic Instrument, DESI, have revealed subtle hints that dark energy might be evolving over cosmic time, potentially strengthening as the universe expands. If this phantom energy behavior continues, dark energy could eventually overpower gravity, electromagnetic forces, and even nuclear forces themselves. In the Big Rip scenario, cosmic expansion accelerates without limit until it tears apart every structure in the universe. The process would unfold with terrifying swiftness once it begins. Approximately 200 million years before the Big Rip, galaxy clusters would dissolve as dark energy overcomes their gravitational binding. Solar systems would disintegrate about 60 million years later as planets drift away from their stars. 3 months before the final moment, Earth itself would be torn from the Sun's gravitational embrace. In the final moments, the fabric of space would expand so rapidly that it rips apart atoms themselves. Chemical bonds would snap, atomic nuclei would fly apart, and even the quarks within protons and neutrons would be separated by the explosive expansion of space itself. The Big Rip would occur not in some distant cosmic future, but potentially within 20 to 100 billion years, soon enough that intelligent beings might witness their universe's violent disintegration. Mathematical models of phantom dark energy suggest that if this scenario unfolds, it would represent not just the end of structure but the end of spacetime itself. The energy density of space would diverge toward infinity, creating conditions where neither matter nor spacetime could exist in any recognizable form. The universe would end not with the gradual cooling of heat death, but in a cosmic crescendo of acceleration that destroys the very concepts of distance, duration, and physical law. Cyclic universe models propose a radically different cosmic fate where the Big Bang represents not the beginning of everything but merely one phase in an eternal cycle of expansion and contraction. According to these theories, Our current epoch of expansion will eventually give way to cosmic contraction as dark energy evolves or new physics emerges to reverse the accelerating expansion. The universe would collapse back toward a cosmic crunch, potentially triggering a new Big Bang that initiates another cycle of cosmic evolution. These ekpyrotic or cyclic scenarios suggest that cosmic history consists of infinite repetitions where universes expand, evolve, contract, and are reborn in endless succession. Each cycle might last trillions of years, with the formation of galaxies, stars, planets, and perhaps life and consciousness recurring in each iteration. The apparent fine-tuning of physical constants might result from an anthropic selection process operating across infinite cycles, where only universes with observer-compatible physics persist long enough to be observed. Yet recent analysis by physicists including Alan Guth and Alexander Vilenkin has revealed fundamental problems with cyclic cosmology. Their calculations show that cyclic models cannot be past eternal within general relativity. Even cyclical universes must have ultimate origins. Moreover, the thermodynamic problems that plague heat-death scenarios also affect cyclic models. Entropy increases with each cycle, eventually preventing the universe from completing additional cycles and returning it to heat-death conditions. Some theorists propose that quantum effects near cosmic bounce points might reset entropy and enable eternal cycling. Yet these proposals require exotic physics beyond current theoretical understanding. The cyclic universe remains an elegant possibility but faces mounting mathematical challenges that may ultimately prove insurmountable within known physics. Before the Big Bang, competing theories propose radically different scenarios that challenge our most basic concepts about temporal sequence and cosmic causation. Alan Guth's eternal inflation theory suggests our universe represents one of infinitely many pocket universes, spawned by never-ending cosmic expansion. In this scenario, cosmic inflation never completely ends but continues forever in most regions of spacetime, occasionally creating bubble universes like our own where inflation stops and normal cosmic evolution begins. According to eternal inflation, our Big Bang was not the beginning of everything but rather a local phase transition in an infinitely expanding multiverse. Sean Carroll notes, "The universe is actually eternal. It existed at all times, so there is no beginning to explain. This perspective suggests that creation and destruction occur continuously throughout the multiverse, with bubble universes constantly forming and evolving while the larger inflationary spacetime continues expanding forever. Yet, eternal inflation faces its own conceptual challenges. If inflation continues forever and spawns infinite bubble universes, then every possible physical law, every possible configuration of matter, every possible history occurs infinitely often throughout the multiverse. This leads to paradoxes about probability, observation, and the nature of scientific explanation that philosophers and physicists continue to debate. Alternative theories propose that the Big Bang emerged from pre-existing quantum vacuum fluctuations, from collisions between higher-dimensional objects called branes, or from the collapse and subsequent rebound of a previous universe. Some models suggest that time itself might be emergent rather than fundamental, arising from more basic quantum geometric processes that operate according to principles we have yet to discover. The implications of cosmic endings for consciousness and meaning represent perhaps the most profound philosophical challenges raised by modern cosmology. If the universe is destined for heat death, if all complexity will eventually succumb to entropy and cold, if consciousness represents only a temporary fluctuation in an ultimately empty cosmos, then what significance can we attach to love, art, scientific discovery, or moral progress? Some philosophers argue that cosmic endings make earthly activities meaningless, that the knowledge of ultimate futility drains life of purpose and value. Yet others contend that meaning emerges from the quality of experience itself rather than its duration, that consciousness and creativity possess intrinsic value regardless of their cosmic longevity. The fact that conscious beings emerged from stardust and learned to contemplate their own cosmic significance might represent triumph enough, independent of whether that consciousness persists forever. Recent advances in computation theory and artificial intelligence have suggested that sufficiently advanced civilizations might find ways to persist even through cosmic endings. Freeman Dyson proposed that intelligence could slow its metabolism to match the universe's cooling, potentially achieving infinite subjective experience within finite cosmic time. More speculatively, advanced civilizations might manipulate spacetime itself, create closed time-like curves that enable escape from cosmic history, or transition to forms of existence that transcend physical limitations. The quest to understand cosmic fate has driven some of the most ambitious scientific projects in human history. The Euclid Space Telescope maps dark energy's evolution across cosmic time, potentially revealing whether phantom energy will trigger a Big Rip. The Vera Rubin Observatory will catalog billions of supernovae to trace cosmic expansion's history and future trajectory. Next-generation gravitational wave detectors may detect primordial signals from cosmic inflation that reveal the multiverse's structure and our cosmic context. These observations carry existential weight that extends far beyond academic curiosity. Understanding whether consciousness faces inevitable extinction or might persist indefinitely affects how we value present experience and future potential. If cosmic heat death is inevitable, should we focus on maximizing immediate well-being? Or does the possibility of cosmic escape justify enormous present sacrifices for future survival? The search for cosmic fate also connects to our understanding of fine-tuning and anthropic selection. If we inhabit one of infinite universes in an eternal multiverse, then our cosmic ending matters less than the continued existence of conscious observers elsewhere in the vast ensemble of realities. Conversely, if consciousness represents a unique cosmic achievement that occurs only rarely, then its preservation becomes a cosmic imperative that transcends individual or even species survival. As we stand at the threshold of becoming a spacefaring civilization capable of influencing cosmic evolution on astronomical scales, these questions transition from philosophical speculation to practical consideration. Whether we direct our efforts toward maximizing present flourishing or toward ensuring long-term cosmic survival depends partly on our understanding of what endings await the universe that gave us birth. In confronting the universe's ultimate fate, we confront the deepest questions about existence, meaning, and our cosmic responsibilities. The same universe that enables consciousness through extraordinary fine-tuning appears destined for endings that render all achievements temporary. Yet perhaps in this very tension between cosmic grandeur and cosmic futility, between the extraordinary precision that enables complexity and the inexorable processes that will eventually destroy it, we find not meaninglessness but profound significance. The universe gave rise to beings capable of understanding their own cosmic context, of measuring the very constants that govern reality, of contemplating the ultimate fate of everything they cherish. In this achievement, consciousness emerging from cosmic evolution to understand cosmic evolution, we may find meaning that transcends duration. Whether the universe ends in fire or ice, whether consciousness persists or perishes, whether meaning endures or dissolves, the fact that such questions can be asked at all represents an extraordinary triumph of matter over meaninglessness, of awareness over indifference, of understanding over cosmic silence. In the end, the universe's greatest mystery may not be dark matter or quantum mechanics or consciousness itself, but the simple fact that existence gave rise to beings capable of wondering about existence at all. In our quest to understand cosmic fate, we participate in the universe's attempt to understand itself, a quest that transforms us from mere observers of cosmic mystery into active participants in the grandest story ever told,